Welcome to the ultimate guide to mastering Scratch, where learning meets relaxation. Find a cozy spot, lean back, and let the gentle rhythm of this tutorial start to wash over you. Close your eyes if you like, or simply let the soothing sounds of coding lull you into a peaceful state. As we explore the world of Scratch together, remember to hit that like button and subscribe for more calming coding adventures. Let the journey begin. Scratch is a visual programming language designed to help users create interactive stories, games, and animations. It was developed by the MIT Media Lab with the goal of making coding accessible to beginners, especially children and young learners. Unlike traditional programming languages that require memorizing complex syntax, Scratch uses a block-based interface where users can drag and drop pre-made code blocks to build programs. This approach simplifies the learning process by focusing on logic and creativity rather than worrying about typos or formatting errors. Scratch is widely used in classrooms and online communities to teach fundamental programming concepts in a fun and engaging way. The Scratch interface consists of several key components that work together to create projects. The blocks palette is the area where you find all the code blocks organized into categories such as motion, looks, sound, and control. The stage is the central area where your project is displayed and tested, acting as the canvas for your animations or games. The sprite list shows all the characters or objects in your project, allowing you to select, edit, or add new sprites. Finally, the code area is where you assemble your scripts by dragging and dropping blocks from the palette. These elements combine to provide a structured yet flexible environment for building interactive content. The blocks palette is divided into different categories, each containing specific functions to control your project. Motion blocks allow you to move sprites around the screen, such as making them move forward, turn, or glide to a new position. Looks blocks let you modify a sprite's appearance, like changing its size, switching between costumes, or displaying text. Sound blocks enable you to add audio elements, such as playing a sound effect or a music track. Control blocks manage the flow of your program, including loops that repeat actions, conditions that make decisions, and events that trigger specific behaviors. Each category is designed to help you build complex interactions step by step. The stage serves as the background where all the action takes place, and it can be customized with different scenes or backdrops. Sprites are the characters or objects that interact within the stage, and each sprite can have multiple costumes to create animations or changes in appearance. For example, a cat sprite might have different costumes for walking, sitting, or jumping. Backdrops are the different scenes or settings that can be switched to create a dynamic environment, such as moving from a forest to a cityscape in a game. Together, the stage, sprites, costumes, and backdrops form the visual foundation of any Scratch project. Scratch introduces core programming concepts through its intuitive block-based system. Events are triggers that start or stop actions, such as when the green flag is clicked or when a key is pressed. Variables are used to store and manipulate data, like keeping track of a player's score or a timer. Loops allow you to repeat actions, such as making a sprite move continuously or performing a task multiple times. Conditions enable decision-making, like checking if a player has collected an item or if a certain condition is met. These concepts form the building blocks of programming and help users understand how to create responsive and interactive projects. Creating your first Scratch project is a straightforward process that encourages experimentation. Start by selecting a sprite from the built-in library, or create a new one using the Paint editor. Then, drag blocks from the Blocks palette into the code area to build scripts that control the sprite's behavior. For example, you might use a motion block to move the sprite and a looks block to change its appearance. Once your code is ready, test it by clicking the green flag, which starts the project. It's important to save your work regularly to prevent losing progress, especially as you add more complex features to your project. Scratch plays a crucial role in learning programming by making abstract concepts tangible and accessible. It eliminates the need to memorize syntax, allowing learners to focus on problem solving and creative thinking. By building projects, students develop skills in logic, sequencing, and debugging, while exploring their interests in storytelling, art, or game design. The foundation laid by Scratch prepares learners for more advanced text-based languages like Python or JavaScript by teaching them core principles such as variables, loops, and conditions. Additionally, Scratch's online community fosters collaboration, as users can share their projects, provide feedback, and learn from others' work. creating a supportive environment for growth and innovation. Sprites are the characters or objects that bring your Scratch projects to life. They can be anything from a friendly animal to a spaceship or a simple shape. The stage is the background where all these sprites interact, creating the environment for your animations and games. Understanding how sprites and the stage work together is key to building dynamic and engaging projects. Whether you're designing a story or a game, these two elements form the foundation of your creative ideas. Sprites are versatile tools in Scratch that you can move, resize, and program with custom scripts. For example, you might have a sprite that represents a character, an animal, or even a background object like a tree or a car. Each sprite has its own set of costumes, which are the different looks it can have and sounds that it can play. This means every sprite can be uniquely designed and controlled, allowing for rich and interactive experiences. By learning to work with sprites, you unlock the ability to create complex and personalized projects. The stage serves as the main area where all the action happens. It's like the world where your sprites live and interact. You can change the stage's background to create different scenes, such as a forest, a city, or a space station. This helps in storytelling or game design by setting the scene. The stage also holds global scripts and variables that can affect all sprites at once. For instance, you might use the stage to control the overall score of a game or trigger events that all sprites respond to. Adding and managing sprites is straightforward in Scratch. You can click the Choose a Sprite button to select from a library of pre-made sprites or upload your own images. Once a sprite is added, you can customize it using the Costumes tab to edit its appearance or the Sounds tab to add audio effects. If you want to change the order of sprites on the stage, simply drag and drop them. This helps control which sprite appears in front of others, ensuring your project looks as intended. Each sprite has specific properties that define its behavior and appearance. Costumes are the different visual states a sprite can have, like a character wearing different outfits or a ball changing color. The position of a sprite is determined by its X and Y coordinates on the stage, which you can adjust to move it around. The size of a sprite can be scaled up or down to make it bigger or smaller. The direction of a sprite refers to its rotation angle, which is measured in degrees and can be used to make it face different directions. The stage can have multiple backgrounds to create different scenes or settings. You can switch between these backdrops using the Backdrops tab. To add a new backdrop, you can choose from the library or upload an image from your computer. For example, you might use a backdrop of a beach for one scene and a city for another. You can also use scripts to automatically switch backdrops, like when a character moves to a new location in a game, or when a story transitions to a new part. Sprites and the stage can interact in many ways. For example, you can program a sprite to detect when it touches the edge of the stage and bounce back, or to detect when it collides with another sprite. These interactions are created using blocks like if on edge, bounce, or touching sprite. The stage itself can also trigger events by broadcasting messages or changing variables, which can affect all sprites in the project. This allows for complex and responsive animations and games. Sprites and the stage are the building blocks of any Scratch project. By mastering their properties and interactions, you can create animations, games, and stories that come to life. Practice adding sprites, adjusting their costumes and sounds, and experimenting with how they interact with the stage. The more you explore these elements, the more creative and sophisticated your projects will become. Keep experimenting and let your imagination guide your learning. Backgrounds and costumes are the foundation of visual storytelling in Scratch projects. They create the environment where your characters and actions take place. Think of a background as the setting of a scene, like a forest, a city, or a space station. Costumes, on the other hand, define how a sprite appears, such as different outfits, expressions, or states. Together, they bring life to your creations, making interactions more engaging and narratives more vivid. Whether you're building a game, an animation, or an interactive story, these elements help guide the viewer's experience and make your project more dynamic. To add backgrounds, start by clicking the Backdrops tab in the Sprite Editor. This is where you can choose from a library of preloaded images or upload your own. If you want to create something unique, use the Paint Editor to modify the background. For example, you might draw a sunset or add text to a scene. Uploading custom images allows you to use your own designs, which can make your project stand out. Remember, backgrounds can also be animated or layered to create more complex scenes. So don't hesitate to experiment with different options. Managing costumes involves switching to the Costumes tab, where you can add, edit, or remove different looks for your sprites. Importing images or drawing new costumes gives you creative control over how your characters appear. it's important to rename costumes clearly, such as labeling them Run 1, Run 2, or Happy to keep track of their purpose. If you have unused costumes, deleting them helps keep your project organized. This is especially useful when creating animations or ensuring that only relevant costumes are loaded, which can improve performance. Switching between backgrounds is done using the Switch Backdrop to block found in the Looks category. This block allows you to change the scene instantly, like moving from a beach to a mountain. You can trigger these changes with events, such as when the green flag is clicked or when a key is pressed. The next backdrop block cycles through all the backgrounds in order, which is great for creating transitions like a day-night cycle. Combining these blocks with variables can add more complexity, such as changing the background based on a score or time. To switch between costumes, use the Switch Costume to Block or the Next Costume block. The first is useful for changing to a specific look, while the second creates a sequence, like a walking animation. By using multiple costumes and the Wait block, you can control the speed of the animation. For example, if you have 4 costumes, adding a wait 0.2 seconds between each switch creates a smooth motion. You can also access costumes by their numerical order using the Costume block, which is helpful for precise control in more advanced projects. Events tied to backgrounds and costumes allow your project to respond to changes. The When Backdrop changes to block can trigger actions like playing a sound or moving a sprite when the background shifts. Pairing costume changes with other blocks, such as motion or sound, adds interactivity. For instance, a character might jump when a new costume is loaded, or a background change could start a new level. Creating interactive environments, like a sunrise animation, requires careful planning of transitions to ensure they feel natural and seamless. Advanced techniques involve using variables to track background or costume states, which can help manage complex sequences. Combining costumes with motion blocks can create parallax effects, making backgrounds appear layered and dynamic. Animating sprites with custom costumes and precise timing adds depth to your projects. However, it's important to optimize performance by avoiding unnecessary assets. For example, removing unused costumes or compressing images can prevent lag, especially in larger projects. These strategies ensure your creations run smoothly while maintaining visual appeal. Mastering backgrounds and costumes is essential for creating engaging and interactive Scratch projects. These elements are not just visual tools, but also key to storytelling and user experience. Practice combining them with other blocks to explore new possibilities, like creating a dynamic weather system or a character transformation. Experiment with transitions and animations to refine your skills, and don't be afraid to test different approaches. The more you experiment, the more you'll discover how these tools can bring your ideas to life. Keep exploring and let your creativity guide your projects. Events are the building blocks that set your Scratch projects in motion. Think of them as the starting signals that tell your code when to begin running. For example, when you click the green flag, that's an event that triggers all the scripts associated with it. Triggers, on the other hand, are the specific actions or conditions that cause these events to happen. They could be a key press, a sprite click, or even a message sent from another part of your project. Understanding how events and triggers work is essential because they allow you to control the flow of your program. Without them, your projects would be static and unresponsive. By using events and triggers, you can create dynamic experiences where your characters and objects react to user input or other changes in the environment. This interactivity is what makes Scratch projects engaging and fun to explore. Scratch offers several common events that you can use to start your scripts. The first is when green flag clicked, which is the most basic event and is used to initialize your project when you start it. This is perfect for setting up variables or positioning sprites at the beginning. Another event is when key pressed, which allows your project to respond to keyboard input. For instance, you could make a character move left or right based on arrow key presses. The when sprite clicked event is useful for creating interactive elements, like a button that changes color when you click on it. Finally, the when message received event enables communication between different sprites in your project. This is especially handy for coordinating complex behaviors across multiple characters or objects. Each of these events serves a unique purpose and can be combined to create more sophisticated interactions. Using events in your scripts is straightforward but powerful. To begin, you'll drag an event block, such as when green flag clicked, into the scripting area. This block acts as the starting point for your code. Once you've placed an event block, you can attach other blocks to it to define the actions your project should take when the event occurs. For example, if you use when key pressed, you might attach a move block to make a character move when a key is pressed. Events are like the foundation of your code, providing the entry points for execution. By using multiple events, you can create scripts that respond to different triggers at the same time. This allows for more complex and layered interactions, such as a game that starts when the green flag is clicked and also responds to key presses during gameplay. The key is to plan out how each event will work and what actions it should trigger. Triggers are the specific actions or conditions that activate events, and they come in many forms. For example, a mouse click on a sprite is a trigger that can start a script, while a key press on the keyboard can trigger movement or other actions. Collisions between sprites can also act as triggers, such as when a player's character touches an enemy in a game. Timer events, like repeating a script every few seconds, are another type of trigger that can add rhythm or timing to your project. These triggers ensure that your scripts only run when necessary, which makes your projects more efficient and responsive. Without proper triggers, your code might run continuously or not respond to user input at all. By carefully designing your triggers, you can create projects that feel smooth and intuitive, whether you're building a game, an animation, or an interactive story. Let's take a look at an example of how events and triggers work together in a simple game. Imagine a game where the player moves a character using the arrow keys and earns points by clicking on targets. The when green flag clicked event can be used to initialize the game, such as setting the score to 0 and positioning the character at the starting point. The when key pressed event can then control the character's movement, making it respond to arrow key presses. When the player clicks on a target sprite, the when sprite clicked event can trigger an action, like increasing the score and moving the target to a new location. By combining these events and triggers, you create an interactive experience where the player's actions directly influence the game's behavior. This kind of setup is common in many Scratch projects and demonstrates how events and triggers can bring your ideas to life. To make the most of events and triggers in your projects, follow some key best practices. First, use clear and descriptive names for your events and triggers. This makes it easier to understand your code, especially when working on larger projects. Avoid overlapping triggers that might cause unintended behavior, such as two events responding to the same key press. Test test your events thoroughly by running your project multiple times and checking for unexpected results. This helps catch bugs early and ensures your project works as intended. Additionally, use messages to communicate between sprites, which can help organize complex interactions and reduce conflicts. By following these practices, you'll create more reliable and maintainable projects that are easier to debug and expand. Remember, the goal is to make your code both functional and easy to understand, whether you're working alone or collaborating with others. In summary, events and triggers are essential tools for creating interactive and dynamic projects in Scratch. They allow your code to respond to user input and other changes in the environment, making your projects feel alive and engaging. Mastering these concepts opens up a world of possibilities, from simple animations to complex games and simulations. As you practice using different types of events and triggers, you'll discover new ways to bring your ideas to life. Apply these concepts to future projects to enhance their functionality and make them more responsive to user interactions. With time and experimentation, you'll become more confident in using events and triggers to create the experiences you envision. Keep exploring, keep building, and let your creativity shine through your Scratch projects. Loops are a powerful tool in programming that help automate repetitive tasks. In Scratch, this means you can make your characters or objects perform actions over and over again without having to write the same code multiple times. This not only saves time, but also makes your projects cleaner and easier to manage. The three main loop blocks in Scratch are repeat, repeat until, and forever. Each of these blocks has a specific use case. For example, repeat is great when you know exactly how many times you want something to happen. Repeat until is useful when you want a task to continue until a certain condition is met. And forever is ideal for actions that need to run continuously, like background music or blinking lights. These loops are essential for creating animations, games, and interactive projects because they allow you to create dynamic and engaging experiences. Let me break down the different types of loops in Scratch. The repeat block is straightforward. It runs a set of actions a specific number of times. For instance, if you want a sprite to move forward 10 steps 5 times, you can place those actions inside a repeat block and set the number to 5. The repeat until block is a bit different because it keeps running until a condition becomes true. This is useful when you don't know exactly how many times an action needs to happen. For example, you might want a sprite to keep moving until it reaches the edge of the screen. The forever block, on the other hand, runs indefinitely until you stop it. This is perfect for continuous actions, like a character spinning forever or a background that never stops. Choosing the right loop depends on what you're trying to achieve in your project. Now, let's look at how to use the repeat block. To start, you'll drag the repeat block from the control category in the Scratch editor. Once you have it, you can insert other blocks inside it, such as movement commands, costume changes, or sound effects. For example, if you want a sprite to move 10 steps 5 times, you'd place the Move 10 Steps block inside the Repeat block and set the number of repetitions to 5. The beauty of the Repeat block is that you can adjust the number of repetitions to create different effects. If you want the sprite to move faster, you can reduce the number of steps or increase the repetitions. This flexibility makes the repeat block a go-to tool for creating patterns, sequences, and timed actions in your projects. The repeat until block is another essential tool in your programming arsenal. To use it, you'll place the repeat until block in your code, and then define a condition that must be met for the loop to stop. For instance, if you want a sprite to move until it touches the edge of the screen, you can set the condition to touching edge. The loop will keep running until that condition is true. This is especially useful for scenarios where you need to wait for an event to happen, like a player collecting an item or a character reaching a target. You can also use variables or sensors to control the loop's exit. For example, a game might use a variable to track a score and stop the loop when the score reaches a certain number. This makes repeat until a versatile choice for interactive and responsive projects. The forever block is designed for actions that need to run continuously. This is ideal for things like background music, blinking lights, or a character that spins endlessly. However, since the forever block runs indefinitely, it's important to include a way to stop it. For example, you might add a key press event that stops the loop when the user presses a specific key. To control the speed of the loop, you can combine it with the wait block. For instance, if you want a sprite to spin slowly, you can add a wait 0.5 seconds block inside the forever loop. This ensures the actions don't happen too quickly, making the animation more visible and enjoyable. The forever block is a powerful tool, but it requires careful planning to avoid unintended behavior or performance issues. Nested loops are a more advanced technique that allows you to create complex patterns and sequences. This means placing one loop inside another. For example, you could use a repeat block to draw a square by repeating the movement and turn commands 4 times. But if you want to create a more intricate shape, like a star with multiple points, you might nest a smaller loop inside the larger one. Each loop handles a specific part of the pattern, and together they create the overall effect. It's important to test each loop step by step to ensure they work correctly. If something goes wrong, it can be hard to track down the issue. So adding comments to your code can help you keep track of what each loop is doing. Nested loops are a great way to expand your creativity and tackle more challenging projects. When working with loops, there are several best practices to keep in mind. First, avoid creating infinite loops without a clear exit condition. This can cause your project to freeze or run slowly. Always make sure your loops have a way to stop, even if it's just a key press or a variable change. Second, keep the duration of your loops reasonable. If a loop runs for too long, it can affect the performance of your project, especially on older devices. Third, test your loops with small numbers before scaling them up. For example, if you're creating a loop that runs 100 times, test it with 5 first to make sure it works as expected. Finally, use variables to track loop progress. This makes your code more flexible and easier to adjust later. By following these practices, you'll create more efficient and reliable projects. In conclusion, loops are a fundamental part of programming in Scratch. They allow you to automate tasks, create dynamic interactions, and build complex projects with ease. By mastering the repeat until, and forever blocks, you'll unlock new possibilities for your creations. Whether you're designing an animation, a game, or an interactive story, loops will help you bring your ideas to life. The key to success is practice. Try applying loops to real-world examples, like making a character dance or a spaceship move across the screen. The more you experiment, the more comfortable you'll become with these powerful tools. So keep exploring, keep building, and let loops help you create amazing projects. Good day. Today, we will explore the powerful world of advanced loops in Scratch. Let us begin by revisiting the basic loop structures that form the foundation of our programming journey. The repeat block allows us to execute a set of actions a specific number of times. The forever block runs continuously, ideal for maintaining ongoing processes. The repeat until block repeats until a condition becomes true, offering flexibility for dynamic scenarios. These basic loops are essential, but as projects grow in complexity, we need more sophisticated tools. Advanced loops empower us to create intricate animations, responsive games, and interactive stories. By the end of this session, you will have mastered nested loops and advanced control flow, unlocking new possibilities in your Scratch creations. Let us now delve into the types of advanced loops. The repeat until block is particularly useful when we want to repeat actions until a specific condition is met. For example, we might use it to wait for a user input or a game event. The forever block, as mentioned, runs indefinitely, making it perfect for continuous actions like background music or constant sprite movement. Nested loops, which involve placing one loop inside another, are crucial for creating multi-dimensional patterns, such as grids or spirals. Lastly, loop variables allow us to track and manipulate values during iterations, enabling dynamic changes in our projects. These tools, when combined, offer immense creative potential. Understanding loop nesting is key to building complex structures. Imagine a scenario where an outer loop controls the number of rows in a grid, while an inner loop handles the columns. This layered approach allows us to create patterns that would be impossible with a single loop. For instance, a grid of shapes can be generated by repeating a set of actions for each row and column. The outer loop sets the overall structure, while the inner loop focuses on the details. This concept is fundamental in animations, simulations, and any project requiring repetitive, yet varied behavior. Let us examine practical examples of nested loops. One common application is drawing a grid of shapes, such as a 5x5 arrangement of squares. The outer loop could control the vertical position, while the inner loop manages the horizontal placement. Another example is a spiral pattern, where each iteration of the inner loop adjusts the direction or size of a shape. For synchronized movements, nested loops can coordinate multiple sprites, ensuring they move in harmony. These examples demonstrate how nesting allows us to break down complexity into manageable parts, enhancing both efficiency and creativity. As with any powerful tool, advanced loops come with challenges. Infinite loops can occur if conditions in repeat until blocks are not properly structured. Always ensure that the condition will eventually become true. Overlapping loops may lead to unintended behavior, so use unique variables for each loop to avoid conflicts. Debugging is essential. Adding wait blocks can slow down execution for observation, while showing variables helps track their values in real time. These strategies will help you navigate common issues and refine your projects. Now, let us explore advanced techniques to elevate our projects. Combining loops with conditionals, such as placing an if statement inside a loop, allows for dynamic decision-making. For example, a sprite might change direction based on its position. Lists can be used to store and retrieve data dynamically, such as a sequence of colors for a rainbow animation. Lastly, optimizing performance by minimizing nested loops is crucial. Sometimes, restructuring code to reduce layers of nesting can improve efficiency and readability. These techniques will help you build more sophisticated and efficient programs. The applications of advanced loops extend beyond simple animations. In game development, they can manage enemy spawning patterns, where waves of enemies appear in sequences. For art projects, loops can generate fractal patterns by repeating shapes with slight variations. In interactive stories, loops can repeat dialogue lines with changing parameters, creating a more engaging experience. These real-world examples highlight how mastering loops transforms Scratch into a versatile tool for creativity and problem solving. To conclude, advanced loops are the backbone of complex Scratch projects. By understanding nested loops and control flow, you can create dynamic and interactive experiences. Remember, careful planning and thorough testing are essential when working with multiple layers of repetition. Practice by applying these concepts to real-world scenarios, and you will see significant growth in your programming skills. Thank you for your attention, and happy coding. Conditional statements are a fundamental concept in programming that allow a program to make decisions based on specific conditions. Imagine you are writing a story where the plot changes depending on what the reader chooses. Similarly, in programming, these statements control the flow of a program by executing different sections of code based on whether a condition is true or false. For example, if a player in a game presses a key, the character moves. If not, it stays still. In Scratch, we use the if and if-else blocks to implement these decisions. These blocks act like the decision points in a story, guiding the program's behavior dynamically. At the heart of every conditional statement is a condition, which is a Boolean expression that evaluates to either true or false. Think of it like a yes or no question. If the answer is yes, the program runs the code inside the if block. If the answer is no, it skips that code. And if there is an else block, runs the code inside that instead. For instance, if a character's health is above 0, the game continues. Otherwise, it ends. This binary logic is essential for creating responsive programs that adapt to different scenarios. The if block in Scratch is found in the control category of the block palette. Its syntax is straightforward. If condition, then code. The condition is a block that can include comparisons, variables, or sensors. And the code is the set of actions to perform if the condition is true. For example, if a key is pressed, the sprite moves. This block is perfect for simple decisions, like triggering an action when a specific event occurs. It's like a single fork in a road. Only one path is taken based on the condition. The if-else block in Scratch extends the if block by adding an alternative path. Its structure is if condition, then code, else code. This means the program will execute one set of instructions if the condition is true and another if it is false. For example, if a player's score is higher than 10, a happy face appears. Otherwise, a sad face is shown. This block is useful for scenarios where two distinct outcomes are possible, such as checking if a user has enough points to win a level, or if a character is alive to continue playing. Nested conditional statements allow us to place one if or if-else block inside another, creating layers of decision-making. This is like having multiple questions in a row. For example, if the player is alive, check if a key is pressed, and if so, make the character jump. This structure enables complex logic, such as checking multiple conditions in sequence. In games, this might mean verifying if a player has collected a power-up before allowing them to access a new area. However, nesting too deeply can make code harder to read. So, it's important to balance complexity with clarity. When using conditional statements, it's crucial to follow best practices to avoid errors. First, keep conditions simple and readable. For instance, use score greater than 50 instead of score plus 10 greater than 60, which can confuse the logic. Second, avoid overlapping conditions that might conflict, like checking the same variable in multiple ways. Finally, test your conditions with various inputs to ensure they behave as expected. For example, if a condition checks for a score, test it with values below, at, and above the threshold to confirm it works correctly. These habits help create reliable and maintainable programs. Conditional statements are the backbone of dynamic programming, allowing Scratch projects to respond to user interactions and changing situations. Whether it's a game that reacts to key presses or a story that changes based on choices, these statements bring interactivity to life. By mastering the if and if else blocks, you can create more engaging and responsive projects. Practice is key. Experiment with different conditions and see how they shape the behavior of your programs. The more you explore, the more you'll unlock the potential of Scratch to bring your ideas to life. Complex conditions are a powerful tool in programming that allow you to combine multiple simple conditions using logical operators. These operators help your program make decisions based on more than one criterion, which is essential for creating dynamic and responsive applications. For example, imagine a game where a player needs to collect both a key and a certain number of coins to unlock a door. Without complex conditions, your program would only be able to check one requirement at a time, limiting the possibilities. By using logical operators, you can create scenarios where the program evaluates multiple factors simultaneously, making your code more versatile and realistic. Logical operators are the building blocks of complex conditions. They enable you to evaluate multiple conditions and determine whether a specific action should be taken. The three primary logical operators are and, or, and not. And requires all conditions to be true for the overall statement to be true, making it ideal for scenarios where multiple requirements must be met, or allows for at least one condition to be true, which is useful when you want to trigger an action based on any one of several possibilities. Not, on the other hand, inverts the truth value of a condition, which is helpful for checking the absence of a particular state. These operators always return a Boolean value true or false, which forms the foundation of decision-making in programming. The and operator is used when all conditions must be true for an action to occur. For instance, if a player's score exceeds 100 and their level is higher than 5, they might earn a bonus. This ensures that both criteria are met before the program takes any action. In Scratch, you can access the AND block by navigating to the operator's menu. Once you drag it into your script, you can place other conditions on either side of it. This is particularly useful in games where multiple factors need to align for a specific outcome, such as a character needing both health and a power-up to proceed. The OR operator is used when at least one condition needs to be true for an action to occur. For example, if a player is either red or blue, an event might trigger, such as a special effect or a score increase. This operator is ideal for situations where multiple possibilities can lead to the same result. In Scratch, the OR block is also found in the operator's menu. By using OR, you can create more flexible logic, such as allowing a player to choose between different paths in a game, or triggering an action based on any one of several conditions. The NOT operator is used to invert the truth value of a condition. For example, if a collision is not detected, a character might continue moving. This is useful for checking the absence of a condition, such as determining if a player is not in a restricted area. In Scratch, the NOT block is located in the operator's menu and can be placed around a condition to reverse its outcome. This operator is particularly helpful for creating rules that depend on the negation of a specific state, such as avoiding obstacles or checking for the lack of a certain item. Combining logical operators allows you to create highly sophisticated conditions. For example, a door might open if the player has a key and the door is not locked. This requires using both and not to ensure the correct sequence of events. Parentheses are essential in these cases to control the order of evaluation, as logical operators can sometimes be ambiguous without them. By strategically combining and, or, and not, you can design intricate logic that mirrors real-world scenarios, such as checking multiple criteria for a game mechanic or a conditional puzzle. In Scratch, complex conditions can be implemented through a variety of examples. For instance, a sprite might change color if its x-coordinate is greater than 100, or its y-coordinate is less than 50. This demonstrates how OR can be used to trigger an action based on either of two conditions. Another example is displaying a message if the player's score exceeds 50 and the time remaining is under 60 seconds. These examples highlight how logical operators can be applied to create engaging interactions in games or animations. As a practice exercise, try designing a condition for a game mechanic, such as a character jumping only when they are on the ground and a button is pressed. One common mistake when working with complex conditions is forgetting to use parentheses, which can lead to unexpected results. For example, without parentheses, the order of operations might not align with your intended logic. Another frequent error is misusing AND instead of OR or vice versa, which can cause conditions to be too restrictive or too lenient. Additionally, overlooking the NOT operator can result in logic that fails to account for the absence of a condition. These pitfalls can be avoided by carefully planning your conditions, testing them thoroughly, and using parentheses to clarify the intended sequence of evaluations. To use complex conditions effectively, start by breaking them into smaller, manageable parts. This makes it easier to test and debug each component before combining them. For example, if you're creating a condition that checks multiple factors, test each individual condition separately to ensure they work as expected. When you combine them, you can be more confident that the overall logic is sound. Additionally, adding comments to your code can help you and others understand the purpose of each condition, especially when the logic becomes intricate. These practices will help you write cleaner, more reliable code. Complex conditions are a cornerstone of programming that allow your code to make nuanced decisions. By mastering logical operators like AND, OR, and NOT, you can create programs that respond to a wide range of scenarios. Whether you're designing a game, an interactive story, or an automated system, the ability to combine conditions is essential for solving real-world problems. As you continue to practice, experiment with different combinations of operators and observe how they affect your programs. With time, you'll develop a deeper understanding of how to use these tools to bring your creative ideas to life. Understanding the importance of reusability in programming is key to writing efficient and maintainable code. When we create custom blocks, we can reuse the same set of instructions multiple times, which saves time and reduces errors. By learning to create and use these blocks, you'll be able to build more complex projects with less effort. Procedures, which are sequences of code that perform specific tasks, help organize your scripts so they are easier to read and manage. This approach allows you to break down large problems into smaller, more manageable parts. Custom blocks are user-defined blocks that extend the capabilities of Scratch's built-in functions. These blocks allow you to group together a series of commands that you might need to use repeatedly. For example, instead of writing the same set of instructions every time you want to draw a shape, you can create a custom block that does it for you. These blocks can also include parameters, which are inputs that let you customize their behavior. This flexibility makes your code more dynamic and adaptable to different situations. To create a custom block, start by navigating to the More Blocks category in the block palette. Click the Make a Block button to open the block editor. Here, you'll assign a name to your block and decide if it needs any parameters. For instance, if you're creating a block to draw a square, you might add a parameter for the size of the square. This way, the same block can draw squares of different sizes by simply changing the input value. Once defined, the block appears in the palette and can be used in your scripts like any other block. Once you've created a custom block, using it is straightforward. Drag the block into the script area and connect it to other blocks to define the sequence of actions. For example, if you have a block called Draw a Square, you can place it in your script and connect it to movement or color blocks. The real power of custom blocks lies in their reusability. You can use the same block multiple times in different parts of your project, which makes your code cleaner and easier to modify. This also helps prevent errors that might occur from repeating the same code manually. Procedures are essential for organizing complex scripts. A procedure is a sequence of code that performs a specific task, such as moving a character or playing a sound. Custom blocks act as procedures by encapsulating these tasks into a single, reusable unit. This not only makes your scripts easier to read, but also reduces the chance of errors by isolating functionality. For example, instead of writing the same set of commands to move a character every time, you can create a procedure that does it in one step. This approach keeps your code modular and easier to debug. The benefits of using custom blocks are numerous. They improve code organization by grouping related commands, which makes your scripts more structured and easier to understand. They also enhance efficiency by allowing you to reuse code instead of rewriting it. When a block is tested and working correctly, it becomes a reliable component of your project, making debugging simpler because you can isolate issues to specific blocks. Additionally, custom blocks encourage modular programming, where you build projects by combining small, independent parts, which is a fundamental skill in software development. Custom blocks offer advanced features that can take your projects to the next level. For example, you can use multiple parameters to make blocks more versatile. A block that calculates the area of a rectangle might take both length and width as inputs, allowing it to handle different dimensions. Nested blocks, where one custom block is used inside another, can create complex interactions with minimal code. Sharing blocks across projects is another powerful feature, as it allows you to reuse your creations in different contexts, saving time and promoting consistency. These features enable you to build more sophisticated and dynamic programs. Let's look at some practical examples of custom blocks in action. A play sound block could take a sound name as a parameter, allowing you to trigger different sounds without rewriting the code each time. A calculate sum block might accept two numbers as inputs, making it easy to add values in various parts of your project. A draw star block could use a side length parameter to adjust the size of the star, demonstrating how parameters make blocks adaptable. These examples show how custom blocks can simplify tasks and make your code more flexible and reusable. Avoiding common mistakes is crucial when working with custom blocks. One frequent error is forgetting to define parameters for input values, which limits the block's functionality. Overcomplicating blocks by adding too many functions can make them difficult to use and debug. It's important to keep blocks focused on a single task. Another mistake is not testing blocks thoroughly before integrating them into larger projects. Always verify that a block works as intended in isolation and in different scenarios to ensure reliability. These practices help maintain clean and effective code. Custom blocks and procedures are fundamental tools for efficient coding in Scratch. By practicing their creation and use, you'll develop skills that make your projects more organized and scalable. Experimenting with parameters allows you to unlock advanced functionality, such as dynamic behavior and complex interactions. As you continue exploring, remember that the goal is to write code that is not only functional, but also easy to understand and maintain. Keep building, testing, and refining your custom blocks to enhance your programming journey. Today, we will explore how to reuse code effectively in Scratch by using custom blocks. Custom blocks allow you to create your own commands that can be used multiple times throughout your project. This not only makes your code more efficient, but also helps keep your scripts organized. By the end of this session, you will understand how to create and use custom blocks to streamline your programming tasks. Custom blocks are user-created commands that group together a set of instructions. These blocks can be reused in different parts of your project, which saves time and reduces the need to repeat the same code. For example, if you have a sequence of actions that you use frequently, you can turn it into a custom block. This makes your scripts easier to read and manage, especially when working on complex projects. To create a custom block, start by opening the Blocks palette and clicking the Make a Block option. You will then define a name for your block and decide if it needs any parameters. Parameters allow your block to accept different values, making it more flexible. Once the block is created, you can drag the code you want to include into the block's definition. This code will then be executed whenever the block is used. Using custom blocks offers several advantages. First, they eliminate the need to copy and paste the same code multiple times, which reduces errors. Second, they help simplify complex scripts by grouping related actions into a single block. This makes your code easier to understand and debug. Finally, maintaining your program becomes more straightforward because changes only need to be made in one place. Let me share some examples of how custom blocks can be used. A draw square block might take a size parameter to draw squares of different sizes. A play greeting block could accept a name, input to personalize messages. A calculate area block might perform math operations using inputs like length and width. These examples show how custom blocks can handle repetitive tasks and make your programs more dynamic. When creating custom blocks, follow these best practices. Use clear and descriptive names, such as move right, instead of generic labels like block 123. Include parameters to make your blocks adaptable. For instance, a draw circle block with a radius parameter can be used in various contexts. Lastly, document your blocks with comments or notes to explain their purpose, which is especially helpful when revisiting your work later. In summary, custom blocks are a powerful tool for improving efficiency and organization in your Scratch projects. By learning to create and use them, you can tackle more complex tasks with ease. Practice by identifying repetitive actions in your scripts and turning them into custom blocks. This skill will help you build cleaner, more professional programs as you continue exploring Scratch. Lists in Scratch are a powerful tool for storing multiple values in a single variable, which makes them incredibly useful for organizing data. Think of them as a way to keep track of many items at once, like a grocery list or a collection of scores. Unlike simple variables that hold only one piece of information, lists can hold numbers, text, or even other lists, making them versatile for a wide range of projects. This ability to store and manage dynamic data means you can create more complex and interactive programs, such as games that track player progress or simulations that handle changing conditions. Understanding how to use lists effectively is a key step in mastering Scratch. To create a list in Scratch, you can use the Make a List option in the Variables category. This allows you to define a new list with a name that clearly describes its purpose, such as scores or inventory. Choosing descriptive names helps you and others understand the list's role in your project. Once a list is created, you can add items to it using the Add to List block, which appends a new value to the end of the list. If you need to remove items, the Delete from List block lets you remove specific entries or clear the entire list. These actions are essential for managing data that changes over time, like updating a player's inventory in a game or removing outdated information. Accessing items in a list is straightforward with the Item X of List block, which lets you retrieve specific elements by their position. For example, if you have a list of names, you can get the third name by using the number 3 as the index. The Length of List block is also crucial, as it tells you how many items are in the list, which is helpful when you need to loop through all elements. To do this, you can use the Repeat Length of List block, which runs a set of actions for each item in the list. Additionally, the Sort List in Order block allows you to arrange items in ascending or descending order, making it easier to analyze or display data in a specific sequence. These operations give you control over how data is stored and used in your projects. Lists are commonly used in projects to handle dynamic data efficiently. For instance, in a game, you might use a list to store player scores, allowing you to track high scores or update them as the game progresses. Inventory systems often rely on lists to keep track of items a player collects or uses. Lists can also be used to store user input, such as choices made in a quiz or dialogue tree, making it easy to reference or modify those choices later. Another practical use is generating random selections, like picking a random item from a list of options for a game mechanic or a storytelling feature. By leveraging lists, you can create more engaging and responsive projects. While Scratch does not have true arrays like some programming languages, lists in Scratch serve a similar purpose by allowing you to store and access multiple values. In Scratch, list indexes start at 1, which is different from some languages that use zero-based indexing. This means the first item in a list is always at position 1, and you can access it using the Item 1 of List block. For more complex data structures, you can use nested lists, where one list is stored inside another, effectively mimicking multi-dimensional arrays. Combining lists with variables can also create advanced data structures, such as a list of scores for different players or a grid of game elements. These techniques allow you to handle more intricate projects with greater flexibility. In conclusion, lists are a fundamental part of Scratch programming, enabling you to organize and manipulate data in ways that enhance your projects. Mastering list operations allows you to create more dynamic and interactive programs, from simple score tracking to complex simulations. Practicing with lists in real-world scenarios, such as building a game or a quiz, helps solidify your understanding and improves your ability to solve problems. Experimenting with nested lists and advanced operations like sorting or filtering adds layers of complexity to your projects. By continuing to explore the possibilities of lists, you can unlock new creative potential in your Scratch creations. Today, we will explore advanced list manipulation in Scratch, a powerful tool for managing complex data sets. Lists allow you to store multiple values in a single variable, making it easier to handle large amounts of information. This skill is essential for creating dynamic and responsive programs, such as games with inventories or apps that track user interactions. By the end of this session, you will have mastered techniques to insert, sort, and filter data, enabling you to tackle more sophisticated projects. Let's begin by understanding how lists work. In Scratch, a list is like a container that can hold many items at once. Each item in a list has a unique position called an index, which starts at 0. For example, the first item in a list is at index 0, the second at index 1, and so on. Lists can store numbers, text, or even other lists, making them incredibly versatile. This structure allows you to organize data efficiently, such as keeping track of a character's inventory or storing a sequence of commands for a sprite to follow. Now, let's dive into advanced list operations. You can insert items at specific positions, which is useful for maintaining order in a list. Sorting a list in ascending or descending order helps organize data for easier access. Reversing a list can be handy when you need to display items in the opposite sequence. Additionally, removing duplicates or specific elements ensures your data remains clean and relevant. These operations are fundamental for tasks like ranking scores or filtering out unwanted information. Conditional list processing combines loops, and if statements to filter data based on criteria. For instance, you might count how many items in a list meet a certain condition, such as numbers greater than 10. This technique allows your program to respond dynamically to user input, updating the list in real time. Imagine a quiz app that highlights correct answers, or a game that adjusts difficulty based on player performance. By using conditionals, you can create more interactive and intelligent Scratch projects. Nested lists take list manipulation to the next level by allowing lists within lists. This structure is ideal for representing complex data, such as coordinates in a 2D space. For example, a list of X, Y pairs can store the positions of multiple objects. To access a specific coordinate, you use two indices, the first for the outer list and the second for the inner list. This approach is essential for applications like mapping systems or game boards, where multiple attributes need to be tracked Simultaneously, efficient list management is crucial for optimizing your Scratch projects. Avoid performing unnecessary operations, such as repeatedly sorting a list when it's already ordered. Use temporary variables to store intermediate results, reducing the risk of errors. Additionally, optimize loops by minimizing iterations and using efficient block combinations. These practices not only improve performance, but also make your code easier to debug and maintain, ensuring your programs run smoothly even with large datasets. Let's explore real-world applications of advanced list manipulation. In game development, lists can manage a player's inventory, storing items like weapons or potions. For a quiz app, lists track scores and user responses dynamically. Simulations often rely on lists to organize data, such as tracking weather patterns or population growth. By mastering these techniques, you can create projects that handle complex scenarios with ease, making your Scratch programs more engaging and functional. Troubleshooting common issues is an essential skill. Index out-of-bounds errors occur when you try to access an item that doesn't exist, such as using a number larger than the list length. Always check the size of your list before accessing elements. Incorrect data types, like adding a string to a list of numbers, can cause unexpected behavior. Use the Show List block to visualize your list's contents and identify issues quickly. Debugging with these tools ensures your programs behave as intended. Now, let's apply what we've learned. Start by creating a list of numbers, such as 5, 2, 9, 1. Use the sort block to arrange them in ascending order. Then, filter even numbers by looping through the list and checking each value. Finally, display the results in the sprite's costume using the Say block, or by changing the costume based on the filtered data. This exercise will reinforce your understanding of list operations and prepare you for more complex challenges. To recap, we've covered advanced list techniques, from inserting and sorting to nested structures and troubleshooting. These skills are vital for creating dynamic and efficient Scratch projects. By experimenting with nested lists and conditional processing, you can unlock new possibilities in your programs. Remember, practice is key. Don't hesitate to explore and test your ideas. Happy coding. Cloning in Scratch is a powerful feature that allows you to create multiple copies of a single sprite. This technique is especially useful when you need to generate repeated elements in your games or animations without having to manually create each one. For example, if you're designing a game where multiple enemies appear on the screen, cloning can help you efficiently produce these elements. Importantly, clones can either behave exactly like the original sprite or have unique behaviors. This flexibility means you can program clones to move in different directions, change colors, or perform actions that differentiate them from the original, adding depth and variety to your projects. Cloning in Scratch works by creating a copy of a sprite that functions independently. Unlike creating a new sprite from scratch, a clone is an instance of the original, meaning it shares the same code and properties, but can have its own unique actions. The primary tool for this is the Make a Clone of Myself block, which is found in the Control category of the block palette. When you use this block, the clone inherits the current position, costume, and variable values of the original sprite. However, clones are not separate sprites in the project editor, so they don't appear as individual entries in the sprite list. This makes cloning an efficient way to manage multiple similar elements without increasing the complexity of your project. To create a clone in Scratch, you use the Make a Clone of Myself block. This block is typically placed in a script that triggers when a specific event occurs, such as a key press or a timer. For instance, imagine a sprite that represents a bullet in a game. When the player presses the spacebar, the sprite can use the Make a Clone of Myself block to create a bullet clone at its current position. The clone will then inherit the original's costume, position, and any variables it has. This means the clone starts with the same appearance and data as the original, but it can later be programmed to move in a different direction or change over time, allowing for dynamic interactions in your project. When working with clones, the When I Start as a Clone block is essential. This block is part of the Events category and triggers a set of actions specifically for the clone. It allows clones to perform unique tasks, such as moving in different directions or changing their behavior based on their environment. For example, if you have a sprite that creates clones to represent stars, each clone can use the When I Start as a clone block to move in a random direction or fade out after a few seconds. This block also works well with the broadcast feature, enabling you to send messages to all clones at once, such as instructing them to disappear or change their appearance. Combining these tools gives you greater control over how clones interact with your project. Cloning has a wide range of applications in Scratch projects. One common use is creating enemies in games, where multiple copies of a single enemy sprite can spawn at different locations and follow unique paths. Another example is generating stars or snowflakes in animations, where clones can be programmed to fall or twinkle in different patterns. Cloning is also useful for simulating crowds or particles, such as creating a crowd of people moving in a scene or particles like fire or smoke. These examples demonstrate how cloning can simplify complex tasks by allowing you to replicate a single sprite's behavior while adding variations through individual scripts. This technique not only saves time, but also makes your projects more dynamic and visually engaging. While cloning is a powerful tool, it can lead to some common challenges. One issue is clones overlapping if they are created in the same location or move without proper spacing. To avoid this, you can program clones to move away from the original or use random positions when they are created. Another challenge is memory overload, which occurs when too many clones are generated and remain active. To prevent this, use the delete this clone block to remove clones when they are no longer needed, such as after they have moved off the screen or completed their task. Testing clones in different scenarios is also crucial to ensure they behave as intended. For example, check if clones disappear correctly, if they move as expected, and if they don't interfere with other elements in your project. In summary, cloning in Scratch is a versatile technique that enhances creativity by allowing you to duplicate sprites efficiently. It enables you to create complex interactions by combining clones with events, variables, and other blocks. Whether you're designing games, animations, or simulations, cloning can save time and add variety to your projects. To master this feature, practice creating and managing clones in different contexts, such as spawning enemies, generating particles, or simulating crowds. By experimenting with clones, you'll discover new ways to bring your ideas to life and make your projects more engaging and dynamic. Scratch is a powerful tool that allows you to add sound and music to your projects, making them more immersive and engaging. The sound category in the block palette offers a variety of tools to manipulate audio, giving you creative control over how sounds are used. This category includes access to a built-in sound library, which has a wide range of pre-recorded sounds, as well as the ability to record your own sounds using a microphone or upload custom audio files. These features enable you to create unique auditory experiences that enhance your projects. Whether you're designing a game, a story, or an interactive animation, sound plays a crucial role in capturing the audience's attention and bringing your ideas to life. By incorporating sound, you can add emotional depth, provide feedback, or even guide users through your project's narrative. The sound block in Scratch provides several options for playing audio. The play sound block is used to trigger a selected sound immediately, which is ideal for background music or instant sound effects. For example, you might use this block to start a background track as soon as your project begins. The play sound until done block, on the other hand, plays a sound and then pauses the program until the sound finishes. This is useful when you want the program to wait for a sound to complete, such as a voiceover or a specific audio cue. To use these blocks, you can drag and drop sounds directly from the sound library or upload your own custom sounds. The sound library contains a variety of sounds, including music tracks, ambient noises, and effects, which can be easily integrated into your project. Experimenting with different sounds can help you find the perfect fit for your creative vision. When it comes to adding sound effects, the start sound block is perfect for short, quick sounds like a bird chirp, a door creak, or a game alert. This block allows you to play a sound effect without interrupting the flow of your program. If you need to stop all sounds immediately, the Stop All Sounds block is your go-to tool, which is especially useful in games or interactive stories where sudden silences are needed. The sound library has a wealth of pre-recorded effects, such as meow, ding, or swoosh, which can be used right away. Additionally, Scratch includes a microphone tool that lets you record your own sounds, giving you the freedom to create personalized audio elements. Whether you're designing a video game or a digital story, these sound effects can add layers of realism and interactivity to your work. Creating music in Scratch is straightforward with the play note block, which allows you to play individual musical notes. For example, you can use C4, E4, or G4 to create a simple melody. The tempo block adjusts the speed at which these notes are played, letting you control the rhythm of your music. By combining multiple play note blocks in sequence, you can build complex melodies or harmonies. To fine-tune the timing between notes, the wait block is essential, as it introduces pauses that help create a natural flow. For instance, you might use a wait block to space out notes in a song or to create a beat in a game. With these tools, you can experiment with different musical patterns and create original compositions that bring your projects to life. Advanced sound techniques in Scratch allow for more dynamic control over audio elements. The change volume and set volume blocks let you adjust the loudness of sounds, which is useful for creating fading effects or balancing audio levels in a project. The set pan block adds a stereo panning effect, making sounds appear to come from the left or right side of the speaker. These features can be combined with events like when green flag clicked to trigger specific audio actions at the start of a project. Additionally, using variables to control sound parameters opens up new possibilities, such as adjusting volume based on user input or changing the panning effect dynamically. By integrating these techniques, you can create more immersive and interactive experiences that respond to the user's actions in real time. In summary, sound and music are essential components of Scratch projects, adding depth, interactivity, and creativity. Mastering key blocks like play sound, play note, tempo, and volume controls allows you to enhance your projects in meaningful ways. Experimenting with sound effects and music can help you develop unique auditory elements that elevate your work. Don't be afraid to combine sound blocks with other features, such as events or variables, to create dynamic and engaging experiences. Practice is the key to unlocking the full potential of sound in Scratch. So keep exploring, testing, and refining your ideas. With time and creativity, you can transform your projects into rich, multimedia experiences that captivate your audience. Collaboration is a powerful way to enhance creativity and learning, because when people work together, they bring diverse perspectives and ideas to the table. In the Scratch programming language, this is especially true because the platform is designed to foster teamwork and shared projects. Whether you're working on a game, animation, or interactive story, collaborating with others allows you to combine your strengths and learn from each other. Understanding how to collaborate effectively in Scratch also prepares students for real-world projects where teamwork is essential. By practicing collaboration, students develop communication skills, problem-solving abilities, and a deeper appreciation for the creative process. Sharing your projects on the Scratch website is a great way to connect with the global community of creators. When you publish your work, others can see, play, and even remix your projects, which can lead to valuable feedback and inspiration. The Share button is your gateway to making your projects public or private, depending on your needs. For public projects, you can invite others to explore and engage with your work. To make your projects more discoverable, take the time to add detailed descriptions, relevant tags, and clear instructions. These elements help others understand your project and increase the chances of it being viewed and appreciated by a wider audience. Remixing is one of the most exciting features in Scratch because it allows users to take an existing project and build upon it. This process encourages learning by example, as you can study how others have structured their code and then modify it to suit your own ideas. To remix a project, simply click the Remix button, which creates a copy of the original project that you can edit freely. However, it's important to always give credit to the original creator when you remix their work. This not only respects their effort, but also helps maintain a positive and collaborative community where everyone feels valued. Scratch offers a range of collaborative editing features that make working with others seamless and efficient. The Collaborate feature allows multiple users to work on the same project in real time, which is perfect for group assignments or creative brainstorming sessions. To manage permissions, you can assign roles such as editor or viewer, ensuring that everyone has the appropriate level of access. Additionally, the collaborative editor includes tools to track changes and leave comments, making it easier to review progress and provide feedback. These features help teams stay organized and focused while working on complex projects. Version control and history are crucial for managing changes to your Scratch projects. Scratch automatically saves every version of your project, allowing you to roll back to a previous state if something goes wrong. The History tab is a powerful tool that lets you view past edits, compare changes, and restore specific versions of your project. By saving milestones, such as key stages of development, you can keep your work organized and track your progress over time. This feature is especially useful when working on long-term projects or when multiple people are contributing to the same project. Communication and feedback are essential components of successful collaboration in Scratch. The Scratch forums and comment sections provide a space for users to discuss their projects, ask questions, and share ideas. When giving feedback, it's important to be constructive and specific, highlighting what works well and suggesting ways to improve. Engaging in collaborative challenges or group projects can also help build teamwork skills and foster a sense of community. By actively participating in discussions and offering support to others, you contribute to a positive and dynamic learning environment. Following best practices for collaboration ensures that your projects run smoothly and that everyone involved feels respected. Clear communication is key, whether you're discussing ideas, assigning tasks, or resolving conflicts. Documenting your code with comments and sharing detailed instructions helps others understand your work and build upon it effectively. Additionally, always respect others' contributions by giving proper credit and adhering to the community guidelines. These practices not only enhance the quality of your projects, but also promote a culture of trust and mutual support among Scratch users. Collaboration and sharing are fundamental skills that every Scratch user should develop. By using features like remixing, collaborative editing, and feedback tools, you can create more innovative and impactful projects. Remember that working with others not only improves your technical skills, but also teaches you how to communicate, problem solve, and think creatively. As you continue exploring Scratch, take the opportunity to engage with the community, share your work, and collaborate on new ideas. These experiences will help you grow as a programmer and a team player, paving the way for even greater achievements in future projects. Debugging is the process of finding and fixing errors in code. When we write programs in Scratch, we often encounter issues that prevent our projects from working as intended. These issues can be categorized into three main types: logic errors, syntax errors, and runtime errors. Logic errors occur when the code runs but doesn't produce the expected result, like a sprite moving in the wrong direction. Syntax errors happen when the blocks are not connected properly, such as missing or mismatched blocks. Runtime errors occur during the execution of the program, like an infinite loop or a division by zero. It's crucial to approach these problems methodically, as even small mistakes can disrupt the entire project. By developing a systematic troubleshooting mindset we can ensure our programs run smoothly and achieve their intended purpose. To debug in Scratch, we follow a series of steps that help us identify and resolve issues efficiently. The first step is to identify the problem by observing what the program is doing versus what it should do. For example, if a character isn't responding to a button press, we need to check the corresponding event blocks. Next, we isolate the code by testing individual sections of the script to pinpoint where the error occurs. This might involve commenting out parts of the code or using the Stop All block to reset the project. Using the debugger tool allows us to step through the code line by line, watching how variables change and where the flow might be breaking. After making adjustments, we test and iterate by making small changes and retesting to ensure the fix works without introducing new issues. Finally, documenting the solution helps us remember what was done and prevents similar problems in the future. Scratch provides several tools to aid in debugging. The green flag and Stop All blocks are essential for resetting the project to its initial state, ensuring that tests are conducted from a clean slate. The pen blocks can be used to visualize a sprite's movement or track variable values, which is helpful for understanding how the program behaves visually. Broadcast messages allow us to trace how events trigger actions in the project, making it easier to see if a message is sent and received correctly. Variables and lists are critical for monitoring data during execution, so checking their values at different stages can reveal where the program deviates from expectations. These tools work together to give us a comprehensive view of our project's behavior. When troubleshooting logical errors, we need to carefully examine the conditions and flow of our scripts. For instance, if a sprite isn't moving when it should, we might check for incorrect operators in a conditional statement, such as using less than instead of greater than. The order of blocks in a script also matters. Placing a wait block before a move block can prevent the sprite from jumping too quickly. Using say or think blocks can help us track the decision-making process, like displaying a message when a condition is met. Testing edge cases, such as inputting 0 or extremely large numbers, ensures the program handles all possible scenarios gracefully. These steps help us uncover hidden flaws in the logic of our code. Fixing syntax errors requires attention to the structure of the blocks. One common issue is leaving gaps between blocks, which can cause the program to skip parts of the code. For example, if a repeat block is not properly connected to the blocks inside it, the loop might not execute as intended. Missing wait blocks can also lead to rapid, unintended actions, like a sprite spinning too fast. Additionally, we must ensure all required parameters are provided, such as numbers or variables, to avoid errors. By carefully reviewing the connections and parameters in each block, we can resolve these issues and ensure the code is syntactically correct. Runtime errors often arise during the execution of a program and can be more challenging to predict. To avoid infinite loops, we must include exit conditions that allow the loop to terminate, such as a counter reaching a specific value. Division by zero is another common problem, which can be prevented by checking if the divisor is zero before performing the operation. Using if-then-else blocks helps handle unexpected user input, like ensuring a number is entered before proceeding. By anticipating these scenarios and adding safeguards, we can make our programs more robust and less prone to runtime failures. Adopting best practices for debugging can significantly improve the efficiency of our workflow. Breaking complex projects into smaller, manageable parts allows us to test each section individually, making it easier to identify issues. Adding comments to explain the purpose of scripts helps others and ourselves understand the code's functionality later. Collaborating with peers to review code can uncover mistakes we might have overlooked. Finally, maintaining clear naming conventions for variables, sprites, and costumes keeps the project organized and reduces confusion. These practices not only streamline debugging, but also enhance the overall quality of our Scratch projects. Debugging is an essential skill for creating reliable and functional Scratch projects. By using tools like the debugger, pen blocks, and broadcast messages, we can effectively identify and resolve issues in our code. Patience and systematic testing are key to uncovering errors, as even small mistakes can have significant consequences. Applying best practices, such as breaking projects into smaller parts and keeping code organized, helps prevent future problems. With consistent practice, we can become more confident in our ability to troubleshoot and refine our creations, ensuring they work as intended. Welcome to this session on building a simple game using the Scratch programming language. Today, we will explore the process of creating a maze game, a fun and interactive way to learn essential programming concepts. Game development is a powerful tool for understanding how code works because it combines creativity with logic, allowing you to see immediate results of your efforts. As we progress, you will learn how to use sprites to represent characters, program movement to control their actions, detect collisions between objects, and implement logic to create a working game. These skills are fundamental not only for game design, but also for broader programming applications. Let's dive into the basics of game elements and how they come together. To create a game, we need to define its core components. The player is the character you control, often using keyboard inputs like arrow keys or the WASD keys. The maze consists of walls and paths that the player must navigate, acting as obstacles and guiding the player toward the goal. The goal is the target you must reach, such as a flag or a star, which signals the completion of the game. Optional elements like a score or timer can add an extra layer of challenge and engagement. For example, a timer might encourage players to complete the maze quickly, while a score could reward them for avoiding obstacles. These elements work together to create an immersive experience. Let's move on to setting up the game environment. The first step in building your game is to set up the stage, which serves as the background of your maze. You can choose a pre-designed maze from the Scratch library or create your own using the Paint editor. Adjusting the stage size ensures that all elements are clearly visible, especially if your maze is complex. The stage panel allows you to customize the environment further, such as adding lighting effects or changing the background color. A well-designed stage enhances the visual appeal and usability of your game. Once the stage is ready, we can focus on creating the player sprite. Now let's create the player sprite. Start by selecting a character from the Scratch library, such as a cat, an arrow, or a custom image you design. You can also draw your own sprite using the Paint editor. Next, program the movement by using event blocks like when up arrow key pressed, and change Y by 10 to move the sprite up. Similarly, you can assign other keys to move left, right, or down. It's important to test the movement to ensure it feels smooth and responsive. For example, adjusting the number of steps in the Change Y by block can control the speed. This basic movement is the foundation of player interaction in your game. Designing the maze requires careful planning. Use the paint editor to draw walls and paths, making sure to distinguish between them visually. A clear start and end point are essential to guide the player through the maze. Test the layout by playing through it to ensure it's navigable without being too easy or too difficult. For instance, if the maze is too narrow, the player might get stuck, while a maze with too many open spaces might lack challenge. Balancing complexity and clarity is key to creating an enjoyable experience. Once the maze is complete, we can add obstacles to increase the challenge. Obstacles are critical for making the game more engaging. Create additional sprites, such as rocks or barriers, and position them strategically within the maze. Use the if touching obstacle V. Then stop all block to prevent the player from passing through these obstacles. This collision detection ensures the game remains challenging. For example, if the player touches an obstacle, the game might reset, or the player might lose a life. Testing these interactions is crucial to ensure they work as intended. Obstacles add depth to the game, encouraging players to think critically about their movements. The goal is the destination the player must reach to win the game. Design a target, such as a star or a flag, and program a win condition when the player touches it. For instance, use the if touching goal V, then show you win message block to display a victory message. You can also add a sound effect to celebrate the achievement. This feedback reinforces the player's success and provides a satisfying conclusion to the game. The goal should be clearly visible and placed in a location that requires the player to navigate the maze effectively. Implementing game logic involves using variables to track progress, such as a score or a timer. For example, create a variable called score and increment it when the player collects items or completes tasks. A timer can be added using the start timer and time blocks to measure how long it takes the player to reach the goal. To allow the game to restart, use the when green flag clicked block to reset all variables and return the player to the starting position. These elements add structure and replayability to your game, making it more dynamic. Testing is a vital step in the development process. Playtest your game to identify any bugs, such as the player passing through walls or the goal not triggering correctly. Adjust the movement speed, maze size, or obstacle placement based on your findings. For example, if the maze is too large, the player might get lost. so consider reducing the size or adding visual cues. Ensuring the game is both fun and challenging requires balancing difficulty and accessibility. Regular testing helps refine the experience for players. Enhancing your game can make it more engaging. Add sound effects, like a click when the player moves or a ding when they reach the goal, to create an immersive atmosphere. A timer can increase difficulty by limiting the time available to complete the maze. For added complexity, introduce multiple levels or power-ups that the player can collect, such as a speed boost or the ability to pass through obstacles temporarily. These features encourage creativity and keep players interested in exploring new challenges. When issues arise, troubleshooting is essential. Check for incorrect event triggers, such as a key press not linked to the correct movement. Verify that collision detection works by testing interactions between the player and obstacles. Use the debug mode to step through your code and identify errors. For example, if the player can pass through a wall, review the "if touching" block to ensure it is correctly configured. Debugging helps ensure your game runs smoothly and provides a satisfying experience for players. To recap, we have covered designing the game environment, programming movement, creating obstacles, and implementing logic to make the game functional. Experimenting with new ideas is encouraged as it fosters innovation and deeper understanding. Future sessions will explore advanced game mechanics, such as animations and complex interactions, to expand your skills. Remember, game development is an iterative process, and each project builds on the previous one. Keep exploring and enjoy the journey of creating your own games. Platformer games are a classic genre where players navigate a character through a side-scrolling environment. These games typically involve actions like jumping over obstacles, climbing, and avoiding hazards. The core idea is to create a dynamic world where the player interacts with the environment. Common elements include a player character, platforms that the character can stand on, enemies that pose challenges, and a scoring system to track progress. By the end of this session, you will have built a basic platformer game using Scratch, which will help you understand the fundamental mechanics behind these types of games. Our goal today is to create a fully playable platformer game in Scratch. We will start by programming the character's movement, allowing it to move left and right and jump over obstacles. Next, we will add platforms which will serve as the foundation for the game world. We will also introduce enemies and hazards to make the game more challenging. Finally, we will implement a scoring system to keep track of the player's progress. Throughout the process, we will test and debug the game to ensure it runs smoothly and is fun to play. The game will feature several key elements. The player sprite is the main character, which you will control. You can design it to look like a cat, a robot, or any other character you choose. Animations will make the character's movements more engaging, such as walking or jumping. Platforms are the structures the player can stand on, which can be static or moving. Enemies, like bugs or traps, will add challenges, while the score and timer will track how well the player performs. Together, these elements create an interactive and dynamic game experience. To begin, we need to set up the game stage. Choose a background that matches the theme of your game, perhaps a forest, a city, or a space setting. Use the paint editor to draw platforms or select pre-made sprites from the library. Position the platforms to create a path the player can navigate. For a scrolling effect, we will use code to move the background and platforms as the player moves. This creates the illusion of a larger world and keeps the game engaging as the player progresses. Next, we will create the player sprite. Start by selecting or drawing a character. You can use the paint editor to design a unique look or choose from existing sprites. Add multiple costumes to create animations, such as a walking cycle or a jumping pose. Using Scratch's motion and control blocks, we will program the character to move left and right with arrow keys, or the W and D keys. The jump action will involve a combination of changing the Y position and simulating gravity to make the movement feel natural. For movement, we will use the arrow keys, or W and D for left and right. The jump mechanic requires a bit more detail. When the player presses the up arrow, the character will move upward, but gravity will pull it back down. This is achieved by using a change Y by block and a weight block to simulate the effect. Collision detection is crucial when the character lands on a platform. We need to stop the downward movement. This ensures the character stays on top of the platforms and avoids falling through. Adding platforms involves more than just placing them on the screen. To create a scrolling effect, we will use the if on edge bounce block to make the background move as the player progresses. We will also create variables to track the positions of platforms, which helps in organizing the game world. Some platforms can be static, while others can move, like elevators or sliding blocks. This adds variety and keeps the game interesting as the player navigates through different challenges. Enemies and obstacles are essential for creating challenges. Design enemy sprites with unique behaviors, such as moving back and forth or appearing at specific intervals. Program their movement using loops and conditional statements. For example, an enemy might move left and right continuously. When the player collides with an enemy, the game should respond by triggering a game over. This adds tension and encourages players to avoid hazards while navigating the game world. Scoring and lives are key to tracking the player's progress. Create variables called score and lives to keep track of these values. Increase the score when the player collects items or reaches certain points in the game. Decrease the lives when the player collides with enemies or falls into a pit. When the lives reach 0, the game ends, prompting the player to try again. This system provides a sense of achievement and challenges the player to improve their performance. Testing and debugging are critical steps in game development. Playtest the game to identify issues like the player falling through platforms or enemies moving incorrectly. Adjust parameters such as speed, gravity, or collision detection to fix these problems. Adding sound effects for jumps, collisions, and background music enhances the overall experience. These elements make the game more immersive and engaging for players. In summary, we have covered the essential elements of platformer games, from designing the stage to programming movement, adding enemies, and implementing scoring systems. Remember, game development is a creative process. Experiment with new ideas like power-ups or special abilities to make your game unique. Share your projects with others to get feedback and continue improving. The skills you've learned today will help you create more complex games in the future. Interactive stories are narratives where the audience makes decisions that shape the outcome. Imagine a tale where the user chooses the next action, leading to different paths and endings. In Scratch, we bring these stories to life using sprites, which are characters or objects, backdrops that set the scene, and programming blocks that control interactions. By combining these elements, we create dynamic experiences where users feel involved. Engagement and user interaction are crucial in game design because they keep players invested and make the experience memorable. Whether it's a simple adventure or a complex simulation, the ability ability to respond to user input transforms passive viewing into active participation. Every interactive story relies on key elements to guide the narrative. Characters are the heart of the story, so we design sprites with unique traits, like distinct costumes or behaviors, to make them relatable. Dialogue is conveyed through the say block, allowing characters to speak or share thoughts, which adds depth to their personalities. Choices create branching paths, and we use if-else logic to determine what happens next, like a decision to turn left or right. Consequences tie these choices to changes in the story, such as a character's mood shifting or the environment altering, which makes the experience feel responsive and meaningful. Before coding, we need to plan the story's structure. Start by outlining the beginning, middle, and end, much like a traditional story. Identify key decision points where the user's choices will matter, and brainstorm possible outcomes for each. A flowchart helps visualize how scenes connect, making it easier to spot gaps or inconsistencies. Assigning roles to sprites and backdrops ensures clarity, like designating one sprite as the narrator and another as the protagonist. This planning phase lays the foundation for a cohesive and engaging story. Scratch blocks are the tools that bring the story to life. Begin with the when green flag clicked block to start the story when the user clicks the green flag, similar to launching an app. Use broadcast and receive blocks to transition between scenes, like moving from a forest to a castle. Variables track important information, such as the user's score or a character's health, allowing the story to adapt. Combine loops with wait blocks to create timed events, like a countdown or a delayed action, adding rhythm and suspense to the narrative. Interactivity makes the story feel alive. Design buttons or keyboard inputs, like pressing the spacebar to advance the plot, to give users control. If-else statements respond to these inputs, creating a dialogue where the story reacts to choices. Test transitions between scenes to ensure they flow smoothly, avoiding abrupt jumps that might confuse the user. Sound effects and music enhance immersion, like a dramatic score during a climax or a soft melody during a peaceful moment, making the experience more engaging. Testing is essential to polish the story. Playtest it to find errors, like a scene that doesn't load or a choice that doesn't work as intended. Gather feedback from others to identify areas for improvement. such as unclear instructions or unbalanced decisions. Adjust timing, dialogue, or logic based on user experiences, ensuring the story is both functional and enjoyable. Save the project regularly and share it with peers for additional insights, creating a collaborative environment to refine the work. Recap: the process involves planning the story, coding the interactions, testing for issues, and refining based on feedback. Creativity and problem solving are at the core of interactive storytelling, as each decision impacts the overall experience. Don't hesitate to explore advanced features like custom blocks to streamline complex tasks or add unique effects. The goal is to experiment and grow. So ask questions, practice regularly, and let your imagination guide the story's direction. Today, we will explore advanced animation techniques in Scratch, which allow you to create more complex and engaging visual experiences. These techniques go beyond basic movement and introduce tools for dynamic interactions. By mastering these concepts, you can bring your projects to life with realism and creativity. The key topics we will cover include sprite manipulation, which lets you control characters with precision, custom blocks for organizing code, physics simulations to mimic real-world motion, and multi-layered effects to add depth to your animations. These skills will empower you to design more sophisticated and interactive projects. Sprite animation is a cornerstone of dynamic visuals in Scratch. Frame-by-frame animation involves using multiple costumes to create the illusion of motion, such as a character walking or a ball bouncing. To achieve smooth transitions, you can use timing blocks like wait or change effect to control how quickly costumes switch. Motion and rotation can add realism, for example, making a sprite rotate as it moves or tilt when turning. Clones take this further by allowing you to create multiple instances of a sprite, which is useful for effects like a crowd of characters or a swarm of insects. Combining these techniques can lead to rich, layered animations that captivate your audience. Custom blocks are powerful tools for improving code efficiency and reusability. By creating your own blocks with parameters, you can encapsulate complex actions into simple commands. For instance, a jump block might take a parameter for height, allowing you to adjust it easily across different sprites. Organizing code with custom blocks keeps your project modular, making it easier to debug and scale. Testing these blocks thoroughly ensures they work reliably in various scenarios. For example, a spin block could be used for a dancer or a spinning top, demonstrating how custom blocks streamline repetitive tasks. Physics simulations in Scratch enable you to create realistic motion effects. Gravity can be simulated by continuously adjusting a sprite's Y position, while velocity and acceleration control how fast and smoothly it moves. Variables are essential for tracking motion data, such as speed or direction. Collision detection involves checking the distance between sprites and using conditionals to trigger actions like bouncing or stopping. Adding friction might involve gradually reducing velocity over time, mimicking real-world resistance. These techniques can bring life to games and interactive stories by making movements feel natural and responsive. Multi-layered animation techniques help create a sense of depth and complexity. By layering sprites, you can separate elements into foreground, midground, and background, which enhances visual storytelling. The Go to Z block allows you to control the stacking order of sprites, ensuring the right elements appear in front. Parallax scrolling adds movement to backgrounds by adjusting their speed relative to the foreground, creating a 3D effect, combining layers with timed events, such as fading in a background after a scene transition, can produce seamless and immersive animations that feel dynamic and alive. To refine your animation skills, start by planning your animations with storyboards or flowcharts to visualize the sequence of events. Variables can act as switches to control animation speed, behavior, or even trigger specific actions. Testing your animations iteratively helps identify issues and improve smoothness. For example, adjusting a variable might slow down a character's movement for better visibility. Exploring Scratch's tutorials and community projects can also provide inspiration and new techniques. Remember, practice and experimentation are key to discovering unique ways to apply these methods. In summary, advanced animation techniques in Scratch include mastering sprite control, leveraging custom blocks for efficiency, simulating physics for realism, and using multi-layered effects to create depth. These tools not only enhance the visual appeal of your projects, but also encourage creative problem solving. As you continue, embrace experimentation and challenge yourself to build more intricate original animations. The possibilities are endless, and the more you practice, the more confident you will become in transforming ideas into dynamic, interactive experiences. Today, we will explore the creative process of customizing costumes and backdrops in Scratch. Visual design plays a crucial role in making projects engaging and visually appealing. By mastering these elements, you can transform basic ideas into dynamic and immersive experiences. Our session objectives include learning how to edit existing costumes, add new ones, and enhance visuals to elevate your projects. We will also discuss practical techniques to refine your designs and bring your creative vision to life. Costumes are the visual identities of sprites, such as characters or objects, and they define how these elements appear and behave in your project. Backdrops, on the other hand, serve as the backgrounds that set the scene and establish the overall atmosphere. Together, these elements shape the aesthetic and user experience of your work. A well-designed costume can convey emotions or actions, while a thoughtfully crafted backdrop can immerse the audience in a specific environment. Understanding how to manipulate both will give you greater control over your project's storytelling and interactivity. To add new costumes, start by selecting the sprite you want to customize. Click on the Costumes tab in the Sprite Editor, where you can import images from the library or upload your own files. The library offers a wide range of pre-made images, but uploading your own allows for unique personalization. Once imported, you can use the Paint tool to draw new costumes or modify existing ones. This process gives you the freedom to create characters that match your project's theme or adjust visuals to fit specific needs. The Paint Editor is a powerful tool for editing costumes. Use the brush to add details, the eraser to remove parts, the color picker to match hues, and the shape tools to create geometric elements. You can also adjust the size, rotation, and transparency of your designs to achieve the desired effect. For example, making a costume partially transparent can create a ghostly effect or blend it with the background. Remember to save your changes to ensure they are applied to your project. These adjustments can significantly enhance the visual quality of your sprites. For backdrops, navigate to the Backdrops tab in the Stage Editor. Here, you can add new backdrops by selecting from the library or uploading images. The Switch Backdrop to Block allows you to change scenes dynamically in your code. This feature is essential for creating transitions between different environments or levels in your project. By planning your backdrops carefully, you can guide the audience's experience and create a more cohesive narrative. Customizing backdrops follows similar principles to editing costumes. Use the paint editor to add text, graphics, or even animations. For instance, you might design a cityscape with moving cars or a sky with clouds that drift across the screen. Layers are particularly useful for managing overlapping elements, such as ensuring sprites appear in front of the background. This technique helps maintain clarity and visual hierarchy, making your project more polished and professional. Advanced techniques involve adjusting the sea order of sprites to control which elements appear on top of others. This is vital for creating complex scenes where multiple characters or objects interact. Animated backdrops can be created by using multiple frames, allowing for smooth transitions or background movements. Combining these methods with costume animations can lead to interactive and visually rich experiences. For example, a character walking through a changing landscape can feel more dynamic and engaging. Customizing costumes and backdrops is a key skill that empowers you to express creativity and enhance user engagement. By practicing editing, adding, and animating visuals, you will unlock new possibilities for your projects. Whether you're designing a game, a story, or an interactive art piece, these skills will help you build unique and immersive worlds. Apply what you've learned today to bring your ideas to life with greater visual impact and technical precision. Good day. Today, we will explore the pen and motion blocks in Scratch. These blocks are essential for creating dynamic projects where sprites can draw and move on the stage. The pen blocks allow sprites to leave trails, while the motion blocks control their movement. By the end of this session, you will understand how to use these blocks individually and combine them to create intricate designs and animations. We will start by examining the pen blocks and their functions, then move to the motion blocks. Finally, we will see how these two categories work together to bring your ideas to life. Let's begin. The pen blocks in Scratch give sprites the ability to draw on the stage. The pen down block starts drawing when the sprite moves. So imagine a turtle leaving a line as it walks. The pen up block stops the drawing, allowing the sprite to move without leaving a trail. The change pen color block adjusts the color of the pen incrementally, while the set pen color block lets you choose a specific color. The clear block erases all drawings, which is useful for resetting the stage. These blocks are fundamental for creating art and visual effects. Remember, the pen down is crucial for any drawing activity. The motion blocks control how a sprite moves across the stage. The Move X Steps block moves the sprite forward by a specified number of steps, like a car driving straight. The Turn X Degrees block rotates the sprite clockwise, which is useful for changing direction. The Go to XY block positions the sprite at exact coordinates, similar to placing a piece on a grid. The Point in Direction X block sets the sprite's orientation, with 0 degrees facing right, 90 up, and so on. The Glide X Seconds to XY block smoothly moves the sprite to a location, creating a more natural motion. These blocks are the foundation for controlling sprite movement. Let's see the pen blocks in action. If you use the pen down block followed by the move block, the sprite will draw a line as it moves. For example, moving forward 100 steps while the pen is down creates a straight line. The pen up block can be used to stop drawing temporarily, like lifting a pencil. A practical exercise is to create a simple shape, such as a triangle. Start with pen down, move forward, turn 120 degrees, repeat 3 times, and you'll form a triangle. Experiment with different pen colors and sizes to make your drawings more expressive. Now, let's explore the motion blocks in action. The Turn block can rotate a sprite, which is useful for changing direction. For instance, turning 90 degrees allows a sprite to make a right angle. Combining the Move and Turn blocks enables complex paths, like creating a spiral or a zigzag. To practice, try programming a sprite to move in a circle by turning a small angle repeatedly. Alternatively, use alternating turns and moves to create a zigzag pattern. These exercises help you understand how motion blocks can guide a sprite's journey across the stage. Combining pen and motion blocks unlocks more creativity. For example, to draw a square, you can repeat the Move and Turn blocks 4 times, each time turning 90 degrees. Using the repeat block makes this process efficient. This technique can be expanded to create polygons with more sides, or even a spiral, by gradually increasing the distance moved. The key is to plan the sequence of movements and turns. Try creating a spiral by combining increasing steps with small rotations. The possibilities are endless when you blend these blocks. Advanced techniques involve using variables to control pen color or movement. For instance, a variable could change the pen color with each step, creating a gradient effect. Combining pen and motion blocks with if-then blocks allows conditional drawing, such as drawing only when a certain condition is met. Experimenting with the glide block adds smooth animations, making the sprite's movements more fluid. These methods enhance your projects by adding interactivity and complexity. Don't hesitate to explore new combinations. Common mistakes to avoid include forgetting to use pen down before drawing, which results in no trail. Overlapping lines can occur if the motion path isn't planned, so sketching the route first is helpful. Not resetting the pen with the clear block before new drawings can lead to clutter. Always check that the pen down is active when you want to draw, and use clear to start fresh. These tips will help you create cleaner and more intentional projects. Now it's time for a practice activity. Design a project that uses both pen and motion blocks. For example, a moving car that leaves a trail or a rotating star. Think about how the pen blocks can create the trail and how the motion blocks control the movement. Encourage creativity by trying different shapes, colors, and paths. The goal is to apply what you've learned and explore new ideas. Share your projects with others to see how they approached the task. To recap, the pen blocks allow drawing, and the motion blocks control movement. Combining them creates dynamic and interactive projects. These tools are essential for bringing your ideas to life in Scratch. Keep practicing and experimenting with new combinations. The more you explore, the more you'll discover the potential of these blocks. Happy coding! Today, we will explore the exciting process of building an interactive music player, or DJ app, using the Scratch programming language. This session will guide you through creating a functional application that allows users to control and manipulate sound in creative ways. Our goals are to design an app with essential sound controls, such as play, pause, stop, and loop, as well as incorporate effects and user interaction. By the end of this training, you will gain hands-on experience with sound manipulation, event-driven programming, and creative problem-solving. This project not only enhances your technical skills, but also encourages artistic expression through digital tools. To create a fully functional music player or DJ app, we need several key components. First, we must include sound files such as music tracks and samples that will be played and manipulated. Next, we will add control buttons like play, pause, stop, give users direct interaction with the app. Volume and pitch sliders will allow for real-time adjustments, making the app more dynamic. Visual feedback is also crucial, so we will design elements like waveform animations or beat indicators to show sound activity. Finally, we will create a background or DJ interface sprite to give the app a cohesive and professional look. Each of these components works together to create an engaging user experience. Before diving into coding, we need to set up the project properly. Start by importing sound files through the Sounds tab in Scratch. These files can be uploaded from your computer or selected from the built-in library. Next, create sprites for all the interactive elements, such as buttons, sliders, and visual indicators. Organizing these sprites in the sprites list ensures clarity and makes it easier to manage their behaviors. Additionally, we will use variables to track important values like volume, pitch, and playback status. These variables will help us maintain the app's state and respond to user actions effectively. Now, let's focus on implementing the basic controls that make the app functional. For each control button, use the When Button Clicked block to trigger specific actions. For example, the Play button can use the Play Sound block to start a track, while the Pause and Stop buttons can use Stop All Sounds to halt playback. Timing is important for looping tracks, so we can use the Wait block to control how long a sound plays before repeating. To coordinate actions between different sprites, we will use the Broadcast block, which sends messages to trigger events across the project. These blocks form the foundation of user interaction in our app. For a more advanced experience, we can add features like pitch control and volume adjustment. The Change Pitch by block allows users to modify the pitch of a sound in real time, creating effects like speed changes or harmonies. Volume can be adjusted using Set Volume To for precise control, or Change Volume By for incremental adjustments. To enhance realism, we can implement beat matching using repeat until loops and sound analysis techniques to align the tempo of different tracks. Finally, crossfading between tracks can be achieved by gradually increasing and decreasing the volume of each track, creating a smooth transition. These features add depth and professionalism to the app. Visual effects are essential for making the app engaging and intuitive. We can animate sprites to represent sound waves or beats, using blocks like Change Color Effect or Glide create dynamic animations. A DJ mixer interface can be designed with sliders and buttons that respond to user input, adding a tactile element to the experience. Additionally, background images can be added to give the app a polished and professional appearance. These visual elements not only enhance the aesthetics, but also provide users with clear feedback about the app's state and actions. Once the app is built, thorough testing and debugging are necessary to ensure it works as intended. Test all controls to confirm they respond accurately and smoothly. Check for issues like overlapping sounds or timing mismatches that could disrupt the user experience. Use Scratch's debug mode to track variable values and identify any unexpected behavior. Finally, gather feedback from users to pinpoint areas for improvement. This iterative process helps refine the app and ensures it meets the needs of its audience. To wrap up, we've covered the key features of our music player or DJ app, including sound controls, effects, and visual elements. I encourage you to experiment with additional sounds, effects, and interactions to personalize your project. For those interested in further learning, consider exploring advanced topics like MIDI integration or live sampling to expand the app's capabilities. Thank you for your attention, and I invite you to share your completed projects for peer review and discussion. Let's continue to explore the creative possibilities of Scratch together. Creating a quiz or trivia game in Scratch is an excellent way to engage learners while teaching fundamental programming concepts. By building a quiz, students can practice logic, problem solving, and interactive design. Key elements we will explore include variables to track scores and question numbers, lists to organize questions and answers, conditional logic to check responses, and user interaction to make the game dynamic. Today's session will guide you through designing a quiz from scratch, coding its functionality, and testing it to ensure it works smoothly. Before diving into coding, we need to plan the quiz thoroughly. Start by choosing a theme that interests your audience, such as general knowledge, science, or pop culture. Decide how many questions to include. 5 to 10 is a good range for beginners. Next, outline the structure. Each question should have a prompt, an answer, feedback for the user, and a scoring system. Planning these elements beforehand ensures the game is organized and easy to code. Let's begin by setting up the Scratch project. Open Scratch and create a new project to start fresh. Add a backdrop that matches your quiz theme, like a classroom or a game show set. Create a sprite for the quiz host, such as a character that will ask questions and provide feedback. Then, set up essential variables, a score to track correct answers, a question number to cycle through the list, and an answer variable to store user input. These variables will form the backbone of the game. To store questions and answers efficiently, we'll use a list. Lists allow us to keep multiple items in one place, making it easy to manage all the questions. For example, the first question could be, "What is the capital of France?" with the answer Paris. Add more questions to the list to create variety. Each question and answer pair should be placed in separate list entries, ensuring the game has enough content to keep users engaged. Now, let's display the questions to the user. Use the Say block to show the current question on the screen. Update the question number variable to cycle through the list, ensuring each question appears in order. For example, the message could read, question, number of total questions. This helps the user track their progress and understand how many questions remain. To get user input, use the Ask block to prompt the player for an answer. This block pauses the program and waits for the user's response. Store the input in the answer variable so we can compare it to the correct answer later. This step is crucial for making the quiz interactive and responsive to the user's actions. Checking the user's answer requires conditional logic. Use if-else blocks to compare the stored answer with the correct one. If the answer is correct, increase the score and display a positive message like "well done." If it's incorrect, show the correct answer and provide feedback such as "try again." This ensures the game responds appropriately to different user inputs. Feedback and scoring are essential for a satisfying user experience. Display messages like "correct" or "try again" to guide the user. Update the score variable each time the user answers correctly and show the current score on the screen. Once all questions are answered, reset the quiz to allow the user to play again, ensuring the game is ready for repeated use. Adding a timer introduces an element of challenge. Create a timer variable and use a loop to count down from a set time, such as 30 seconds. When the timer reaches 0, end the quiz and display a message like "Time is up" or "You win" based on the user's score. This feature adds excitement and encourages quick thinking. To testing, and debugging are vital to ensure the quiz works as intended. Run the quiz multiple times to check for errors, such as incorrect answers or variables not updating properly. Test all possible scenarios, including edge cases like typos or unexpected inputs. Fix any issues you encounter to make the game reliable and user-friendly. To make the quiz more engaging, consider adding enhancements like sound effects for correct and incorrect answers. Animate the quizmaster sprite to react to user responses, such as cheering for correct answers or sighing for incorrect ones. You can also let users choose difficulty levels, making the game adaptable for different skill levels. These features elevate the user experience and make the quiz more enjoyable. In summary, we've covered the entire process of creating a quiz game in Scratch, from planning and coding to testing and enhancing it. Remember that creativity plays a big role in game development. Don't be afraid to experiment with themes, features, and interactions. Practice and iteration are key to improving your skills. So keep refining your projects and exploring new ideas. Happy coding. Real-world processes are systems or events that occur naturally or within society, shaping the way we live and interact with our environment. These can range from the way whether patterns influence daily life to the way traffic moves through a city. Understanding these processes is essential, but they can be complex and difficult to observe directly. By simulating them in Scratch, we can break down these systems into manageable parts, allowing us to explore their behaviors through programming. This not only makes abstract concepts more tangible, but also empowers us to experiment with different variables and see how changes affect the overall system. Whether it's modeling the growth of a population or the movement of animals in an ecosystem, Scratch provides a creative and interactive way to bring these real-world phenomena to life. Simulating real-world processes in Scratch offers numerous benefits that go beyond simple coding exercises. It enhances problem-solving skills by challenging us to analyze complex systems and identify the key components that drive their behavior. This process of breaking down a system into smaller, manageable parts teaches critical thinking and helps us approach problems methodically. Additionally, it encourages creativity as we find innovative ways to represent real-life scenarios using sprites, variables, and blocks. Testing hypotheses becomes a hands-on experience, allowing us to adjust parameters and observe how changes ripple through the simulation. This interactive approach not only deepens our understanding, but also makes learning more engaging and dynamic. To create effective simulations in Scratch, we rely on several key concepts. Variables are essential for tracking values that change over time, such as temperature, humidity, or the number of people in a crowd. Loops allow us to repeat actions, like the continuous movement of cars in a traffic simulation, or the gradual growth of a plant. Conditionals enable decision-making, such as determining whether a car should stop at a red light, or if rain should trigger a cloud to move. Broadcasts act as signals to coordinate events, like a traffic light changing color or a storm beginning. Together, these tools form the foundation of any simulation, allowing us to model dynamic and interactive systems with precision and flexibility. The process of creating a simulation in Scratch begins with defining the system. This involves identifying the components and rules that govern the system, such as the behavior of traffic lights in a city. Next, we model the elements by using sprites to represent physical objects, variables to track changing data, and blocks to implement logic. Adding interactions requires using events and conditionals to simulate how different parts of the system respond to each other, like cars stopping at a red light. Finally, testing and refining the simulation is crucial. By adjusting parameters and observing outcomes, we can improve accuracy and ensure the simulation behaves as expected. This iterative process helps us build more realistic and meaningful models. Let's take a look at a weather simulation example. Imagine creating a cloud sprite that represents the sky. We can use variables to track temperature and humidity, which will influence the weather. Loops can simulate rain falling or the sun appearing, creating a dynamic effect. For instance, when the temperature drops below a certain threshold, the cloud might start raining, while higher temperatures could cause the sun to shine. We can also trigger changes based on user input, like clicking a button to simulate a storm, or use time variables to show how the weather evolves throughout the day. This hands-on approach allows us to explore how different factors interact and affect the environment. Another example is a traffic flow simulation. We can use multiple car sprites, each with variables for speed and direction, to mimic real-world movement. Traffic lights can be programmed with conditionals to control when cars stop or go, creating a realistic traffic pattern. To add realism, we can introduce randomness, such as varying the speed of cars or the timing of traffic light changes. This helps simulate the unpredictability of real traffic, making the simulation more engaging and educational. By experimenting with these elements, we can better understand how traffic systems operate and how small changes can impact overall flow. To create effective simulations, start with simple models before adding complexity. This allows you to focus on the core mechanics without getting overwhelmed. Use comments to explain the purpose of variables and blocks, making your code easier to understand and modify later. Testing frequently is essential to catch errors early and ensure the simulation behaves as intended. Finally, collaboration can enhance your work by bringing in new perspectives and ideas. Sharing your simulations with others can lead to improvements and inspire new ways to approach problems. These tips will help you build more polished and meaningful simulations. Simulating real-world processes in Scratch bridges the gap between theory and practice, making abstract concepts more accessible and engaging. It fosters creativity by allowing us to design and test our own models, while also developing critical thinking and technical skills. Whether exploring ecosystems, weather patterns, or urban planning, these techniques open up endless possibilities for learning and discovery. By applying what we've learned, we can create simulations that not only entertain, but also educate, helping us better understand the world around us. Good afternoon. Today, we will explore the exciting world of mobile app development using the Scratch programming language. While Scratch is primarily designed for desktop use, it offers a pathway to create mobile applications through the Scratch mobile app. This session will delve into the unique requirements of mobile app development, such as simplified interfaces and touch-based interactions. We will cover the essential tools, techniques, and best practices to help you transition from desktop to mobile app creation. Whether you are a beginner or experienced user, this presentation will provide insights to enhance your skills in this dynamic area. Before we begin, let me outline the prerequisites for mobile app development with Scratch. First, you will need to install the latest version of the Scratch desktop editor, which ensures access to the most up-to-date features and improvements. Next, download the Scratch Mobile app from the App Store or Google Play to test your projects on mobile devices. A stable internet connection is crucial, as many features rely on cloud-based services for saving and sharing projects. Lastly, a basic understanding of Scratch blocks and project structure will help you navigate the mobile development process more efficiently. These steps form the foundation for creating functional and engaging mobile apps. Now, let's discuss the key differences between desktop and mobile app development. On a desktop, users interact with a mouse and keyboard, while mobile apps require touch-based interactions. This shift necessitates a simplified interface, as mobile screens are smaller and require responsive design to adapt to various resolutions. Additionally, mobile apps have limited access to external libraries or hardware, such as printers or USB devices. Performance and battery efficiency are also critical factors, as mobile devices have constraints on processing power and energy consumption. Understanding these distinctions will guide you in designing effective mobile applications. To set up your mobile app project, start by creating a new project in the Scratch desktop editor. Navigate to the File menu and select the Mobile tab to enable mobile-specific features. This step ensures your project is optimized for mobile devices. Next, design a simple interface using buttons, sprites, and backgrounds that align with mobile usability principles. Finally, test your app using the preview mode in the Scratch Mobile app. This allows you to see how your project functions on a mobile device before finalizing it. These steps will help you build a solid foundation for your mobile application. When designing the mobile interface, prioritize simplicity to enhance user experience. Avoid cluttered layouts by focusing on essential elements. Use large, touch-friendly buttons to accommodate finger interactions and reduce errors. Incorporate visual feedback, such as color changes or animations, to confirm user actions and improve engagement. Organize your app's screens using the back and go to blocks, which help users navigate between different sections seamlessly. These design choices will make your app more intuitive and user-friendly. In coding for mobile interactions, replace mouse events with touch events. For example, use the "when this sprite is touched" block instead of when the mouse is clicked. Utilize variables and lists to manage the app's state, such as tracking scores or user preferences. Implement swipe gestures by combining motion blocks with direction detection, allowing users to interact with your app in dynamic ways. Adding sound effects and animations can further enhance the user experience, making your app more engaging and interactive. These techniques will help you create responsive and lively mobile applications. Testing and debugging your app is a crucial step in the development process. Always test on actual mobile devices to ensure accurate performance, as simulators may not reflect real-world conditions. Check compatibility across different screen sizes and orientations to provide a consistent experience. Use the debug mode in the Scratch Mobile app to identify and resolve errors efficiently. Finally, gather feedback from users to refine your app's functionality and design. These practices will help you create a polished and reliable mobile application. Once your app is ready, publishing it is the next step. Export your project as a SB3 file, which is the standard format for Scratch projects. Upload this file to the Scratch website to share it with others. You can also distribute the link via social media or third-party platforms if you use additional tools. Remember to add a clear description and screenshots to make your app more visible and appealing. These steps will help you showcase your work and reach a wider audience. To conclude, mobile app development with Scratch requires adaptability and creativity. Focus on designing intuitive interfaces and optimizing performance for mobile devices. Explore advanced features like cloud storage or multiplayer interactions to expand your app's capabilities. The best way to improve is through practice. Try building a simple game or utility app to apply what you've learned. With dedication and experimentation, you can create innovative mobile applications that engage users and demonstrate your skills. Thank you for joining this session, and I encourage you to continue exploring the possibilities of Scratch. Scratch is a visual programming language designed for creativity and learning. It allows users to create interactive stories, games, and animations by dragging and dropping blocks of code. However, Scratch's capabilities extend beyond the digital screen when connected to hardware. By integrating hardware, learners can explore the physical world through programming, making abstract concepts tangible. For example, sensors can detect environmental changes, motors can move objects, and and LEDs can light up based on programmed instructions. One popular example of this integration is the microbit, a small computer equipped with sensors, buttons, and LEDs that can be controlled directly through Scratch. This connection opens up new possibilities for hands-on learning and innovation. Connecting Scratch to hardware enhances learning by bridging the gap between the virtual and physical worlds. This approach encourages students to experiment with real devices, fostering a deeper understanding of how software interacts with the physical environment. For instance, a learner might build a robot that responds to sensor input or create a game that uses a microbit's accelerometer to control movement. These projects not only make programming more engaging, but also develop problem-solving skills as learners troubleshoot and refine their creations. The tangible feedback from hardware helps reinforce concepts and motivates continued exploration, making the learning process more dynamic and interactive. To integrate hardware with Scratch, specific tools are required. The microbit is a prime example of a device that works seamlessly with Scratch. It is a compact computer featuring sensors like temperature, light, and motion detectors, along with buttons and an LED matrix. Scratch 3 supports the microbit through the MakeCode extension, which acts as a bridge between the programming environment and the hardware. Connecting the microbit to a computer can be done via a USB cable, allowing direct communication between the two. Some devices also support Bluetooth for wireless connectivity, offering greater flexibility. These tools empower learners to design projects that interact with the real world, expanding the scope of what can be achieved with Scratch. Connecting Scratch to a microbit involves a few straightforward steps. First, the MakeCode extension must be installed in Scratch 3, which enables communication with the microbit. Once the extension is active, the microbit is connected to the computer using a USB cable. This connection allows Scratch to send commands to the microbit, such as displaying a message on its LED screen or reading data from its sensors. For example, a simple block in Scratch could trigger the microbit to light up an LED or play a sound. Testing the connection is essential to ensure everything works correctly, often by running a basic test like lighting an LED or playing a tone. This process provides immediate feedback, helping learners verify their code's functionality. There are numerous creative projects that can be built using the microbit and Scratch. One example is a temperature sensor project where the microbit reads real-time temperature data and displays it on its LED screen or sends it to Scratch for further processing. Another project involves using the microbit's buttons to trigger animations in Scratch, such as making a character move when a button is pressed. The LED matrix on the microbit can be controlled individually, allowing for custom patterns or messages. Additionally, the microbit's accelerometer can detect motion, enabling learners to create games where a character's movement is controlled by tilting the microbit. These projects demonstrate how hardware integration transforms Scratch into a platform for interactive, real-world applications. When encountering issues while connecting Scratch to hardware, several troubleshooting steps can help resolve the problem. First, ensure the microbit is properly connected and powered, as a loose connection can prevent communication. If the device is not recognized, check for updated drivers, which may be required for the computer to identify the microbit. Verify that the Make Code extension is enabled in Scratch, as an inactive extension can block hardware interaction. If communication issues persist, the serial monitor in Make Code can be used to debug the data being sent and received. This tool provides insights into the interaction between Scratch and the hardware, helping identify and fix errors efficiently. Hardware integration transforms Scratch into a powerful tool for real-world applications, allowing learners to create projects that interact with their environment. The microbit serves as a versatile platform for exploring physical computing, offering a range of sensors and outputs that can be controlled through Scratch. By experimenting with sensors, motors, and other devices, learners can expand their creativity and deepen their understanding of programming concepts. The key to mastering hardware interactions lies in practice, connecting, coding, and testing projects repeatedly to refine skills. This hands-on approach not only enhances technical abilities, but also fosters a sense of accomplishment and curiosity, encouraging further exploration and innovation. Scratch is primarily a 2D platform, but can simulate 3D effects through clever programming and design techniques. While Scratch does not natively support 3D models, we can create the illusion of depth by by manipulating sprites and backgrounds. 3D projects enhance immersion and creativity by allowing users to explore spatial relationships and dynamic interactions. This session will delve into techniques such as parallax scrolling, sprite rotation, and perspective layering to create the appearance of a 3D environment. We will also discuss how these methods can elevate the visual and interactive quality of your Scratch projects. Creating 3D sprites in Scratch involves using 2D images that represent 3D objects from different angles. For example, you can convert 3D models into 2D PNGs using online tools or software. Importing sprites from libraries like OpenGameArt provides a starting point for your projects. Once imported, you can animate these sprites by rotating them, scaling them, or adjusting their positions to simulate movement in three-dimensional space. This technique allows for dynamic interactions, such as a car driving forward or a character turning left or right, without requiring full 3D rendering capabilities. To create depth, we can layer backgrounds and foregrounds, mimicking the way objects in the real world appear closer or farther away. By moving background elements slower than foregrounds, we achieve a parallax effect, which enhances the sense of distance. For instance, a distant mountain might move at a fraction of the speed of a tree in the foreground. Variables can be used to control the camera position, allowing the viewer to navigate through the scene. This technique is essential for creating immersive environments, such as a scrolling landscape or a 3D-like tunnel. Applying 3D transforms in Scratch involves using rotation, scale, and skew effects to alter sprites. The rotation block lets you spin a sprite, creating the illusion of movement around an axis. Scaling changes the size of a sprite, which can simulate objects moving closer or farther away. Combining these effects with changes in position allows for more complex illusions, such as a ball bouncing in midair or a spaceship flying through space. Experimenting with these transformations helps users understand how 2D elements can convey 3D motion. 3D sound effects in Scratch can be achieved by adjusting panning and volume based on an object's position. For example, a sound played from the left side of the screen can be panned to the left speaker, while a sound on the right side uses the right speaker. Volume can decrease as an object moves away, simulating distance. Advanced users can explore for more sophisticated spatial audio effects. But even basic adjustments can significantly enhance the realism of your projects. This technique is particularly useful for games or interactive stories with dynamic soundscapes. Designing interactive 3D environments requires layering elements and enabling user input. For instance, you might create a maze where the player navigates through multiple layers of backgrounds, each moving at different speeds to simulate depth. Keyboard or mouse inputs can control the camera or the player's movement, allowing them to explore the space. An example project could involve a 3D obstacle course where the player must avoid moving objects, combining sprite animation, parallax, and responsive controls to create an engaging experience. Advanced techniques involve combining 3D effects with physics simulations, such as gravity or collisions. For example, a falling object can use the gravity block to accelerate downward, while collisions with other sprites trigger specific actions. Custom blocks streamline complex 3D logic, making your code more organized and efficient. Adding lighting and shadows can further enhance realism, even in 2D, by adjusting colors, transparency, or using custom scripts. You can simulate light sources and their impact on the scene, pushing the boundaries of what's possible in Scratch. Performance issues often arise when too many 3D elements are used simultaneously, causing lag or slow interactions. To address this, optimize your code by simplifying sprite designs, reducing the number of active elements, or using efficient scripts. Testing frequently helps identify inconsistencies in depth perception or movement, ensuring a smooth experience. For example, if a sprite appears to jump unpredictably, adjusting its rotation or scale values can resolve the issue. Debugging these challenges is part of the creative process, encouraging users to refine their projects iteratively. Creating 3D projects in Scratch requires a blend of creativity and technical skill. Techniques like parallax, rotation, and sound effects transform 2D tools into powerful platforms for immersive experiences. By experimenting with these methods, you can push the limits of what is possible in Scratch. Remember that the goal is not just to replicate 3D environments, but to innovate and explore new ways to engage users. Keep testing, refining, and sharing your ideas to inspire others and expand the possibilities of 2D programming. Physics principles in programming involve motion, force, and acceleration. These concepts are fundamental to how objects move and interact in both the real world and digital environments. In programming, especially in game development, simulating physics allows for more realistic and engaging experiences. For example, when a character jumps or a ball rolls, these actions rely on the laws of physics. Scratch simplifies these complex ideas by using visual blocks instead of code. Instead of writing equations, you can drag and drop blocks that represent forces and movements. This makes it easier for beginners to grasp the underlying concepts without getting lost in syntax. By using Scratch, learners can experiment with physics in a fun and interactive way, fostering a deeper understanding of both programming and science. Gravity is a force that pulls objects toward a center, like the Earth pulling things downward. In physics, this force is described by Newton's law of universal gravitation, which states that every mass attracts every other mass. For our purposes, gravity in Scratch can be thought of as a constant downward pull. Key variables to track include position, which is where an object is located, velocity, which is how fast and in what direction an object is moving, and acceleration, which is the rate at which velocity changes. In 2D space, gravity primarily affects the vertical movement of objects. For instance, when you drop a ball, it starts with 0 velocity and accelerates downward due to gravity. Understanding these variables helps in creating realistic simulations where objects behave as they would in the real world. To code gravity in Scratch, you need to use variables to track velocity and position. Start by creating 2 variables, such as y velocity and y position, to represent the vertical movement of an object. Then, apply gravity by continuously changing the y velocity. For example, using the block change y by -0.5 simulates a constant downward acceleration. This mimics how gravity affects objects in real life, where their speed increases over time. To make the simulation more dynamic, you can add bounce mechanics. When an object hits the ground, reverse its y velocity and reduce its magnitude to simulate energy loss. This creates a more realistic effect, like a ball bouncing lower each time it hits the ground. By adjusting the values, you can experiment with different gravity strengths and bounce bounce behaviors. Advanced gravity techniques allow for more complex simulations. Variable gravity, for instance, can simulate different planets by adjusting the acceleration value. On the Moon, gravity is weaker, so the acceleration would be smaller, while on Jupiter, it would be much stronger. Combining gravity with other forces, like wind or friction, adds layers of realism. For example, wind could push an object horizontally, while friction reduces its velocity over time. Vectors are essential for multidirectional motion, as they represent both magnitude and direction. In Scratch, vectors can be handled by using separate variables for x and y components. This allows for precise control over how objects move in different directions, enabling scenarios like a rocket navigating through a storm or a spaceship drifting in space. Simulating multiple objects requires organizing data efficiently. Arrays or lists can store information about each object, such as their positions, velocities, and gravity sources. For example, a list might hold the coordinates of multiple gravity points, like planets in a solar system. Managing collisions between objects involves checking their positions and adjusting their movements accordingly. In Scratch, this can be done using loops to compare each pair of objects. However, performance can be a challenge when dealing with many objects. To optimize, use efficient code structures like minimizing nested loops or using variables to store repeated calculations. This ensures the simulation runs smoothly, even with a large number of interacting objects. Collision detection relies on calculating the distance between objects. In Scratch, the distance block measures how close two sprites are. If the distance is less than the sum of their sizes, a collision occurs. Adjusting velocities for collisions involves changing their direction and speed based on the type of collision. Elastic collisions, like a ball bouncing off a wall, conserve energy, while inelastic collisions, like a ball sticking to the ground, lose energy. Visual feedback, such as changing color or size when a collision happens, helps users understand the interaction. By combining these techniques, you can create simulations where objects react to each other in a realistic and visually engaging way. Real-world applications of physics simulations in Scratch are vast. Planetary orbits can be created by applying gravitational forces between objects, mimicking how planets revolve around the sun. Educational games can teach physics concepts through interactive experiments, like testing how different masses affect acceleration. Interactive science experiments might allow users to adjust variables, such as gravity or friction, and observe the outcomes in real time. These applications not only make learning fun, but also help bridge the gap between theoretical concepts and practical understanding. By exploring these examples, students can see how Scratch transforms abstract physics ideas into tangible, hands-on experiences. In summary, gravity simulation in Scratch involves tracking variables, applying forces, and handling interactions. By mastering these techniques, you can create dynamic and realistic environments. Creativity and experimentation are key, as there are countless ways to approach each problem. For instance, you might design a game where players manipulate gravity to solve puzzles, or a simulation that explores the effects of different planetary conditions. As you progress, consider exploring advanced topics like fluid dynamics, where objects interact with liquids or gases. Scratch's flexibility allows for endless possibilities, encouraging learners to push the boundaries of what they can achieve. Keep experimenting and let your imagination guide your projects. Advanced data structures are essential tools for managing complex information in programming. Lists, arrays, and custom structures allow us to store, organize, and manipulate data efficiently. In Scratch, lists are particularly powerful because they can hold multiple values in a single variable, making it easier to handle dynamic data. For example, a list can store a series of scores or a sequence of movements in a game. Arrays, while not a native feature in Scratch, can be simulated using lists to store data in a linear format. Custom structures, on the other hand, let us combine multiple variables to represent complex entities, like a player character with health, score, and position. These structures enhance efficiency by reducing redundancy, improve scalability by handling larger data sets, and offer flexibility to adapt to different programming needs. Understanding them is crucial for building sophisticated Scratch projects. In Scratch, lists are a fundamental way to manage collections of data. To create a list, you can use the Make a List block in the Lists category. Once created, you can add items to the list using the Add to List block, remove items with Delete from List, or access specific items using the Item block with an index number. For instance, if you have a list of names, you can retrieve the third name by using the index 3. Lists are dynamic, meaning they can grow or shrink during runtime, which is perfect for applications like tracking high scores or managing a player's inventory. By mastering list operations, you can create more interactive and responsive programs. Multidimensional lists allow us to store nested data structures, such as grids or matrices, which are useful for representing two-dimensional or hierarchical information. For example, a 2D game grid can be created by having a list of lists, where each sublist represents a row. To access a specific cell in the grid, you would use two indices, one for the row and another for the column. This structure is ideal for games like tic-tac-toe or grid-based puzzles. By using multidimensional lists, you can organize complex data in a way that mirrors real-world scenarios, making it easier to manage and manipulate. This approach also enables more advanced features, such as collision detection or pathfinding in game development. While Scratch does not have native objects or records, we can simulate custom data structures using multiple variables. For instance, to represent a player, you might create variables for health, score, and position. These variables work together to store related information about the player. For more complex scenarios, combining variables with lists can create powerful data management systems. Imagine a list that stores multiple players, each with their own set of variables. This technique allows for scalable and organized data handling, making it easier to track and modify information as your project grows. Custom structures are particularly useful when dealing with entities that have multiple attributes, such as characters, items, or game states. In Scratch, lists can be used to simulate arrays, which are sequential data structures. Arrays are useful for storing and accessing data in a linear fashion, such as a list of numbers or a sequence of commands. To implement sorting algorithms, you can use loops and conditional blocks to rearrange list items based on specific criteria. Similarly, searching algorithms can be created to find a particular item within a list. However, Scratch does not have built-in array functions, so you must create custom scripts for these tasks. This limitation encourages creativity, as you can develop workarounds like using temporary variables or nested loops to achieve the desired functionality. Understanding these techniques helps you leverage lists effectively for more complex projects. Advanced list operations involve using loops to process multiple items in a list efficiently. For example, a loop can iterate through each item in a list to apply a filter, sort the items, or modify their values. Filtering a list might involve checking each item against a condition and retaining only those that meet the criteria, such as selecting high scores from a list of all scores. Sorting can be done using algorithms like bubble sort or selection sort, which compare and rearrange items. These operations are essential for tasks like ranking players, organizing data, or generating dynamic content. By mastering advanced list operations, you can create more intelligent and responsive programs that handle data in sophisticated ways. Best practices for data structures involve organizing your code logically to maintain clarity and efficiency. Use descriptive names for lists and variables, such as player health instead of H, to make your code easier to understand. Avoid clutter by grouping related data together, such as using a list for inventory items rather than separate variables. Testing edge cases is also crucial, such as handling empty lists or out-of-bounds indices, which can cause errors if not addressed. For example, before accessing an item in a list, check if the list has any items to prevent crashes. By following these practices, you ensure your programs are robust, scalable, and easier to debug or modify in the future. To recap, advanced data structures like lists, multidimensional lists, and custom structures are vital for managing complex data in Scratch. Lists allow dynamic data storage. Multidimensional lists enable grid-like organization, and custom structures let you simulate objects with multiple attributes. These tools empower you to build more intricate and efficient programs, from simple games to complex simulations. As you continue exploring Scratch, remember that mastering data structures opens up new possibilities for creativity and problem solving. Experiment with different techniques and don't hesitate to push the boundaries of what you can achieve with these powerful tools. Data visualization is the process of representing information in a visual format to make it easier to understand and analyze. In Scratch, this means using graphics, charts, or animations to turn raw data into something that people can see and interact with. For example, if you have survey results about favorite colors, you could create a bar chart that changes colors as the data updates. The purpose of data visualization is to communicate insights clearly. Whether you're explaining trends, comparing categories, or showing patterns. By using visuals, you can make complex ideas more accessible and engaging for your audience. Before you start building your project, it's important to plan what data you want to visualize. This could be anything from survey responses to weather patterns or even sports statistics. Once you've identified your data, decide on the best way to represent it. A bar chart might work for comparing quantities, while a pie chart is ideal for showing proportions. A line graph could help track changes over time. Your choice should align with the message you want to convey. Also, consider your goals. What do you want your audience to learn or feel? And who is your audience? A younger group might need simpler visuals, while a professional audience could handle more detailed charts. Begin. Set up the Scratch interface by using the stage as your canvas. The stage is where all the action happens, so design your layout first. For example, you might create a background that includes axes for a graph or a blank space for animations. Add sprites to represent elements like bars, pie slices, or data points. These sprites can be custom designed or imported from the Scratch library. Organize your layers so that interactive elements like buttons or labels appear in the right order. This ensures clarity and makes it easier for users to interact with your project without confusion. Interactivity is key to making your project engaging. Use event blocks like when green flag clicked to start your visualization when the user is ready. You can also add user input mechanisms, such as sliders or buttons, to let people filter data. For instance, a slider might let users adjust the time range of a line graph. Animations and sound effects can enhance the experience, like making a bar grow when data is displayed or playing a sound when a user clicks a button. These elements make your project feel dynamic and responsive to the user's actions. Now it's time to bring your data to life. Store your data in variables or lists so it can change dynamically. For example, if you're tracking temperature readings, a list can hold each value and update automatically. Use loops and conditionals to process this data, like looping through a list to draw a bar chart, or using conditionals to highlight specific values. Link the data to visual elements by changing their properties. If a bar's height depends on a number, use a formula to adjust its size. This creates a direct connection between the raw data and the visual representation. Testing is crucial to ensure your project works as intended. Start with sample data to see how your visualization behaves. check for errors in logic, like if a bar's height doesn't match its value, or if a chart updates incorrectly. Also, test the visual representation to make sure it's accurate and easy to understand. Refine animations and interactions for smoother performance. Maybe adjust the speed of a transition or fix a glitch where a sprite disappears. This step helps you catch issues before sharing your project with others. Final touches make your project polished and user-friendly. Add labels, titles, and legends to explain what each part of your visualization represents. For example, a legend could clarify what different colors mean in a pie chart. Include a reset button to let users start over, or a next data button to switch between datasets. Optimize your code by removing unnecessary blocks and organizing your scripts for readability. This makes your project easier to maintain and improves its performance, ensuring it runs smoothly for everyone who uses it. To recap, the key steps are planning your project, setting up the interface, adding interactivity, incorporating data, testing, and refining your work. Each step builds on the previous one to create a functional and engaging visualization. As you gain confidence, experiment with more complex datasets or advanced features like real-time data updates. Sharing your projects with peers can provide valuable feedback and help you improve. Remember, the goal is to make data accessible and interesting through creativity and code. Keep exploring and pushing the boundaries of what you can do in Scratch. Collaborative projects in programming are a powerful way for teams to work together to create complex and innovative programs. When multiple people come together, they bring diverse ideas and perspectives, which can lead to more creative solutions. Sharing responsibilities ensures that no single person is overwhelmed, and it allows each team member to contribute their strengths. Scratch, the visual programming language, offers tools that make real-time collaboration easy. For example, you can share projects directly on the Scratch website, allowing everyone to work on the same project simultaneously. This fosters a sense of community and makes it simple to exchange ideas and feedback as the project develops. Before diving into coding, it is essential to plan the project thoroughly. Start by clearly defining the goal and scope of the project. Ask yourself, what do we want to create? And what are the boundaries of this project? Once the goal is set, break the work into smaller, manageable tasks. This helps prevent the project from feeling overwhelming and ensures that each team member knows their responsibilities. Creating a timeline with deadlines for each phase keeps the project on track and helps everyone stay accountable. Using a shared document, such as a Google Doc or a collaborative whiteboard, is a great way to brainstorm ideas, outline the project structure, and keep everyone aligned. This preparation sets the foundation for a smooth and organized workflow. Assigning roles within a team is crucial for effective collaboration. Common roles include the designer, who focuses on the visual elements and user experience, the coder, who brings the project to life with blocks and logic, the tester, who ensures everything works as intended, and the documenter, who keeps track of the project's progress and documentation. Clearly defining these roles helps avoid confusion and ensures that every task is covered. It is also beneficial to rotate roles if the project allows, as this gives team members the chance to develop new skills and understand different aspects of the project. This flexibility can lead to a more well-rounded team and a stronger final product. Sharing projects on the Scratch website is a straightforward way to enable real-time collaboration. When you share a project, others can access it, edit it, and contribute their ideas. This is especially useful for teams working on the same project from different locations. Comments are a powerful tool for providing feedback or asking questions. For instance, a team member might leave a comment suggesting a change or requesting clarification on a specific part of the project. Keeping the project organized is equally important. Consistent naming conventions, such as using clear labels for sprites and variables, make it easier for everyone to navigate and understand the project. This attention to detail saves time and reduces errors. Version control is a critical practice when working on collaborative projects. To track changes, save copies of the project with timestamps, such as ProjectEV1 or ProjectEV2. This allows you to revisit previous versions if needed. Scratch's Save a Copy feature is particularly useful for this purpose. Before making major edits, it is important to communicate with your teammates to avoid conflicts. For example, if one person is working on the animation while another is updating the code, coordination ensures that their changes do not interfere with each other. Effective version control helps maintain a clear history of the project's development. easier to resolve any issues that arise. Testing and debugging are essential steps in the development process. It is best to test the project incrementally, checking each part as it is completed. This approach helps identify and fix issues early, preventing them from becoming larger problems later. Peer reviews are an excellent way to catch errors that might be overlooked by the person who created them. By having others test the project, you gain fresh perspectives and uncover potential bugs. Scratch provides several tools to aid in debugging, such as the pen blocks for visualizing movement, or the broadcast messages for managing interactions. These tools make it easier to trace and resolve issues, ensuring the project runs smoothly. Maintaining open communication is key to the success of any collaborative project. Use comments on the Scratch website or messaging platforms to share updates, ask questions, or provide feedback. Constructive feedback is especially important. It should focus on the project's goals rather than personal opinions. For example, instead of saying, "This part is bad," say, "This section could be improved by adding a transition." When conflicts arise, it is important to stay focused on the project's objectives and work together to find solutions. By fostering a supportive and respectful environment, the team can overcome challenges more effectively and achieve better results. Finalizing the project involves bringing all the elements together into a cohesive program. This step requires careful attention to ensure that every part of the project works seamlessly. Conduct a final test to check the functionality and usability of the program, making sure it meets the original goal. Once the project is complete, prepare a presentation or documentation to share with others. This might include a step-by-step explanation of how the project works, screenshots, or a video demonstration. Clear documentation helps others understand the project and provides a reference for future improvements or modifications. Taking the time to finalize and present the project ensures that the team's hard work is recognized and appreciated. Collaboration in Scratch not only enhances creativity, but also deepens the learning experience. By working together, team members can learn from each other, share knowledge, and develop new skills. Effective planning, communication, and testing are the pillars of successful collaborative projects. These practices ensure that the team stays organized, addresses challenges proactively, and produces a high-quality final product. As you continue to work on projects, remember that teamwork is a valuable skill that extends beyond programming. By practicing collaboration, you build the ability to work effectively with others, which is essential for future projects and real-world applications. Welcome to the final project planning and design phase of our Scratch programming course. This stage is crucial because it sets the foundation for creating a functional and engaging project. Structured planning ensures that you can manage your time effectively, avoid unnecessary complications, and stay focused on your creative vision. By defining clear goals, outlining step-by-step actions, and organizing resources, you'll be better equipped to tackle challenges and bring your ideas to life. Let's explore how to approach this process systematically. Defining your project scope is the first step in ensuring your work remains focused and achievable. Start by identifying the core idea or theme that excites you. Is it a game, an animation, or an interactive story? Next, consider who your target audience is and what purpose your project will serve. For example, a game for young children will require simpler mechanics than one designed for teenagers. Finally, set clear boundaries to prevent your project from becoming too complex. Ask yourself, what features are essential and what can be omitted to maintain clarity and manageability? Setting clear goals and objectives is essential for tracking progress and staying motivated. Break your project into smaller, manageable tasks, such as designing characters, programming interactions, or testing functionality. Use the SMART criteria to guide your goals. Make them specific, measurable, achievable, relevant, and time-bound. For instance, instead of saying create a game, aim for design a platformer game with 3 levels and 2 playable characters by the end of the week. This approach keeps you focused and provides a sense of accomplishment as you complete each task. Brainstorming ideas and features helps you explore creative possibilities while staying grounded in feasibility. List all the features, animations, or interactions you'd like to include, even if they seem ambitious. Then, prioritize them based on how practical they are to implement and how much they enhance user engagement. For example, a puzzle game might benefit from a timer or sound effects, but adding a complex AI system could be too time-consuming. Consider how each idea contributes to the overall user experience and whether it aligns with your project's purpose. Creating a storyboard or flowchart allows you to visualize your project's structure and sequence of events. Think of it as a roadmap that outlines scenes, character actions, and transitions. For instance, if your project is an adventure game, your storyboard might show the player navigating different levels, interacting with objects, and solving challenges. Use Scratch's stage and sprite tools to sketch these ideas, even if they're rough. This step helps you identify potential gaps and ensures your project flows logically from start to finish. Planning your project structure involves organizing code into logical sections to make it easier to manage and debug. Decide how to separate your code into categories like setup, gameplay, and scoring. For example, the setup section might handle initial conditions, while the gameplay section manages user interactions. Consider what variables, lists, and custom blocks you'll need to track scores, manage game states, or control character behavior. Also, plan how sprites and backgrounds will interact to create a cohesive experience. Choosing the right Scratch blocks is key to adding functionality and interactivity to your project. Use motion blocks to move characters, control blocks to manage loops and conditions, sensing blocks to detect interactions, and event blocks to trigger actions. For example, a loop can make a character move continuously, while a condition can check if the player has collected an item. Avoid using complex blocks without understanding their purpose, as this can lead to errors. Experiment with combinations to find the most efficient solutions. Testing and debugging your plan ensures that your project works as intended. Simulate the project's flow to identify gaps or errors, such as missing interactions or unexpected behavior. Test individual components, like a single level of a game, before integrating them into the full project. Document any issues you encounter, such as a sprite not moving correctly, and revise your plan to address them. This iterative process helps you refine your work and build confidence in your final product. Effective time management and setting milestones help you stay on track throughout the project. Allocate specific time blocks for design, coding, and testing, and set deadlines for each phase. For example, spend the first week on planning and storyboarding, the next 2 weeks on coding, and the final week on testing and revisions. Use a checklist to track progress and ensure you're meeting each deadline. This approach prevents last-minute rushes and ensures you have time to address any challenges that arise. Collaboration and feedback are valuable tools for improving your project. Share your plan with peers to gather suggestions and alternative perspectives. For instance, a classmate might notice an issue with your game mechanics or suggest a more efficient way to code a feature. Incorporate constructive feedback to refine your design and enhance user experience. Scratch's collaborative features, like sharing projects online or discussing ideas in group settings, can also help you learn from others and grow as a programmer. To recap, successful project planning involves defining your scope, setting clear goals, brainstorming ideas, creating visual plans, organizing code, selecting appropriate blocks, testing thoroughly, managing time, and seeking collaboration. These steps ensure your project is well structured, functional, and engaging. Remember, organization is the key to overcoming challenges and achieving your creative vision. Now, it's time to start drafting your own final project plan and bringing your ideas to life. Good luck! Today, we will revisit the fundamental building blocks of Scratch programming. Let us begin with the basics: blocks, events, variables, and loops. Blocks are the visual commands that allow you to control sprites and create interactions. Events trigger actions, such as when the green flag is clicked or a key is pressed. Variables store data that can change during a project, like a score or a timer. Loops enable repetitive actions, such as making a sprite move across the screen or animating a character. Debugging and testing are essential to ensure your projects work as intended. Common issues might include incorrect block sequences, logic errors, or unexpected sprite behavior. By testing your project step by step, you can identify and fix these problems. Organizing your code and sprites helps maintain clarity, especially in complex projects. Use descriptive names for variables and custom blocks, and group related blocks together. This makes your code easier to understand and modify. Let's explore some creative examples. Games like maze challenges or platformers demonstrate how to use events and variables. Animations can bring characters to life with motion and sound. Interactive stories allow users to make choices that influence the narrative. These projects highlight the versatility of Scratch. To earn your certification, you must complete all course modules and submit a final project. The final assessment includes coding tasks that test your understanding of Scratch concepts, as well as theory questions on key topics. For the coding tasks, you will design and implement a project that demonstrates your skills. Theory questions may cover topics like block functions, event triggers, and algorithmic thinking. Submitting your final project involves uploading it to the designated platform. Feedback will be provided to help you improve, so take time to review it and make necessary adjustments. Success in this course requires consistent practice. Review your notes regularly, experiment with new ideas, and don't hesitate to ask for help when you encounter challenges. Collaboration with peers can also enhance your learning experience. After completing the course, you can explore advanced Scratch features. Custom blocks allow you to create reusable code snippets, while extensions add new capabilities like sound effects or hardware integration. Sharing your projects on the Scratch website connects you with a global community. Other users can play, comment, and even remix your work, fostering creativity and collaboration. Learning opportunities extend beyond the course. Workshops, online tutorials, and peer discussions can deepen your understanding. Consider joining Scratch groups or attending virtual events to stay engaged. If you're interested in further programming, Scratch provides a strong foundation for transitioning to languages like Python or JavaScript. The problem-solving skills and logic you've developed will serve you well in these new environments. Now, let's open the floor for questions. Whether you have doubts about the course content, the certification process, or anything else, feel free to ask. Your questions help us improve and support your learning journey. We also encourage you to share your experiences. What aspects of the course were most helpful? What challenges did you face? Your feedback is valuable for future sessions. If you have suggestions for improving the course, such as additional resources or different project ideas, please share them. Your input shapes the learning experience for others. Finally, remember to meet all deadlines for submissions and access resources. Stay proactive in seeking help if needed. Congratulations on completing this course. You've gained valuable skills in Scratch programming and created impressive projects. Take a moment to reflect on how far you've come. Your growth is a testament to your dedication. Keep exploring, experimenting, and coding. The world of programming is vast, and your curiosity will guide you to new discoveries. Thank you for being part of this journey. We look forward to seeing your future projects and continued success. Stay inspired and keep building. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of Scratch will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.